Hello there, and welcome to Science for Sleep, where curiosity gets cozy, distant worlds drift quietly through the dark, and science takes its time. Tonight, we're heading far beyond the familiar spinning ground beneath your feet to visit some of the strangest planets ever discovered. Not the hottest or the biggest, though we may meet a few of those along the way, but the ones that behave like cosmic contrarians. Worlds that looked at the rest of the solar system and decided to spin the other way. Before we settle into that mystery though, I'd love to ask you something simple. Where are you listening from tonight? Is it late evening where you are? Early morning? Perhaps rain is tapping softly against your window, or maybe the night outside is completely still. Somewhere on Earth, someone is waking up under pale sunrise while somewhere else another person is already drifting towards sleep. And meanwhile, the planets above us continue turning in silence, each keeping its own strange rhythm. If you find this voyage calming or interesting, or simply a pleasant way to unwind after a long day, I'd be very grateful if you gave the video a like and maybe subscribed as well. It helps this little corner of quiet science reach more fellow night travellers out there among the blankets and pillows of the world. Now then, get comfortable, loosen your thoughts a little, and let the universe spin slowly around us for a while. Because at first glance, the solar system seems wonderfully orderly. The sun sits at the centre, enormous and steady. The planets move around it in broad looping paths like runners circling a track. Earth spins eastward. Mars spins eastward. Jupiter spins eastward. Saturn does too. Most major planets rotate in the same direction they orbit the Sun, almost as though the entire solar system agreed on a common rule billions of years ago and has politely followed it ever since. And then there's Venus. Venus, the glowing world often called Earth's sister planet, quietly breaks the pattern. If you could stand on its surface, which would admittedly be difficult for several extremely fiery reasons, the sun would rise in the west and set in the east. The planet rotates backward compared to most of its neighbours. Astronomers call this retrograde rotation, which sounds rather elegant for something that basically means that one spins the wrong way. And Venus is not alone in being odd. Farther out, Uranus appears to have tipped over almost completely onto its side. It rotates at such an extreme angle that for long stretches of its year, parts of the planet experience decades of continuous daylight or darkness. Some moons in the solar system orbit backward. Entire exoplanets around distant stars appear tilted, chaotic, or wildly unstable. Suddenly the neat clockwork image of the solar system begins to wobble a little. The universe, it turns out, is not nearly as tidy as old textbooks sometimes make it seem. That may actually be one of the most comforting things about astronomy. Space is not a perfectly synchronized machine where everything behaves exactly as expected. It is full of accidents, collisions, near misses, strange tilts, violent impacts, and ancient catastrophes frozen into planetary motion. Every spinning world carries a history, written not in words, but in rotation. In a way, planets spin like detectives carry clues. A tiny rocky world rotating calmly may have lived a relatively peaceful life. A giant planet tilted sideways might have survived an unimaginable collision long ago. Another world spinning backward could be the survivor of some ancient gravitational disaster that occurred before Earth even had oceans. And what's remarkable is that scientists can often reconstruct these stories from motion alone. That slow turning of a planet, something that feels so ordinary to us because we live on one, contains enormous amounts of information. Rotation reveals how worlds formed, how they collided, how gravity shaped them, and sometimes how chaos won. Earth itself is spinning right now, of course. At this exact moment, whether you're lying in bed, sitting on a couch, or staring sleepily at a ceiling while this plays nearby, our planet is carrying you eastward through space at roughly 1,670 kilometers per hour at the equator, yet you feel absolutely none of it. That fact alone is quietly astonishing. Humans evolved under this spinning, motion so completely that we barely notice it. We think of the ground as stationary and the sky as moving, even though the opposite is true. Sunrise feels like the sun climbing upward, when really it is Earth rotating us gently into daylight. For most of history, people naturally assumed the heavens revolved around Earth because, honestly, it certainly looks that way. The stars wheel overhead. The sun crosses the sky. The moon rises and falls. Earth feels solid and unmoving beneath our feet. But appearances can be wonderfully deceptive. By the time astronomers began understanding planetary motion properly, another mystery emerged alongside the realization that Earth spins at all. Why do planets spin in the first place? It's a surprisingly reasonable question. Nobody walks up to a bowling ball sitting motionless on a shelf and assumes it ought to start rotating on its own. Yet planets do. Entire worlds turn endlessly for billions of years. Where did that motion come from? The answer begins long before planets existed, back when the solar system itself was only a vast drifting cloud of gas and dust. Picture something enormous beyond ordinary imagination. A cold molecular cloud stretching across trillions of kilometers, tiny particles floating in darkness, hydrogen gas, dust grains, frozen compounds, the raw ingredients of future worlds suspended quietly in space. At first, almost nothing happens. Then gravity begins its slow work. A nearby supernova might send shockwaves through the cloud. Slight variations in density begin pulling material inward. Regions collapse. Matter gathers. Slowly, over immense spans of time, the cloud contracts. And something very important happens whenever large clouds collapse. They spin faster. You've probably seen this effect before, even if you never connected it to astronomy. Figure skaters use it constantly. When a skater pulls their arms inward during a spin, they rotate faster because angular momentum is conserved. The same physical law applies to galaxies, stars, hurricanes, and planetary systems. As the giant cloud that formed our solar system shrank, it spun faster and flattened into a rotating disk. That disk became the birthplace of the planets. Everything forming within it inherited that original direction of motion. Dust particles collided and stuck together. Pebbles became rocks. Rocks became planetesimals. Planetesimals merged into protoplanets. Over millions of years, gravity assembled entire worlds. And because nearly everything in the disk was already moving in the same direction, most planets ended up orbiting and spinning the same way. At least most of them did. This is where the story gets interesting, because the early solar system was not peaceful. It was violent beyond comprehension. Young planets smashed into each other constantly. Asteroids collided like cosmic shrapnel. Entire worlds migrated inward and outward. Giant impacts reshaped planetary surfaces repeatedly. Some collisions were glancing blows. Others were catastrophic enough to melt entire planets into oceans of magma. Earth itself likely experienced one such collision. Scientists believe a Mars-sized object called Theia struck the young Earth over 4 billion years ago. The impact was so enormous that debris blasted into orbit and eventually formed the Moon. Which means the Moon, hanging calmly in our night sky, may actually be the surviving aftermath of planetary violence so extreme it reshaped Earth forever. And if impacts like that could happen here, they could happen elsewhere too. In fact, they almost certainly did. A sufficiently large collision can alter a planet's rotation dramatically. Strike a world at the right angle and you might speed it up, slow it down, tilt it sideways, or even reverse its spin altogether. Imagine flicking a spinning top from the side. One hit changes everything. Now scale that idea upward to worlds thousands of kilometers wide, crashing into each other at tens of thousands of kilometers per hour. Suddenly retrograde planets start making a bit more sense. Venus may once have rotated normally before some enormous event altered its spin. Or perhaps powerful tidal interactions with the Sun gradually reversed it over time. Scientists still debate the details because Venus refuses to make things easy. which, honestly, feels very on brand for Venus. Almost everything about that planet is difficult. Its atmosphere is thick enough to crush submarines. Surface temperatures are hot enough to melt lead. Clouds rain sulfuric acid. Probes sent there tend to survive for roughly the length of a moderately patient lunch break before being destroyed. And yet beneath all that hostility, Venus quietly rotates backward, taking 243 Earth days to complete one rotation while orbiting the Sun in only 225, meaning a single Venusian day is longer than its year. If you lived there, birthdays would arrive faster than sunrises. The universe occasionally enjoys little jokes like that. Out beyond Saturn, Uranus presents an entirely different puzzle. Instead of simply spinning backward, it appears almost rolled onto its side. Scientists suspect one or more massive impacts knocked it over early in its history. The result is a planet that essentially rotates like a barrel rolling around the Sun. Imagine Earth tipped sideways so the North Pole pointed roughly toward the Sun. Seasons would become almost unimaginable. Entire hemispheres would spend years facing sunlight continuously, while the opposite side remained trapped in darkness. On Uranus, this actually happens, and yet despite how strange it seems to us, Uranus continues calmly spinning that way as though nothing unusual occurred. Planets, unlike humans, are remarkably unbothered by catastrophic past trauma. What makes all this even more fascinating is that astronomers now know our solar system is not especially unusual. For centuries, humans only had our local planets for reference: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. That was the whole sample size. Then came exoplanets, thousands of them. Suddenly astronomers discovered worlds orbiting multiple stars, planets larger than Jupiter hugging their suns impossibly closely, giant worlds with bizarre elongated orbits, scorching lava planets, frozen rogue planets wandering alone through interstellar darkness, and systems so chaotic they made our solar system look almost conservative by comparison. Some exoplanets may experience rain made of molten glass. Others likely have winds faster than the speed of sound. Certain giant planets orbit so near their stars that entire atmospheres are slowly boiling away into space. Against that backdrop, a backward-spinning planet starts sounding almost modest. The more we discover about the cosmos, the clearer one thing becomes. Nature does not care very much about human expectations. The universe is not obligated to be symmetrical, convenient, or tidy. Gravity creates order, yes, but chaos always sneaks into the story somewhere. Collisions happen, orbits shift, spins tilt. Systems evolve. Sometimes worlds end up facing the wrong direction simply because billions of years ago something enormous hit them at precisely the wrong angle. There's also something strangely relatable about that. A planet's present behaviour often reflects ancient events long gone. The scars remain encoded in motion long after the original collision disappears. In a distant way, planets carry history much like landscapes on Earth do. Mountains reveal tectonic pressure. River valleys preserve erosion. Craters remember impacts. Rotation remembers too. And because astronomy unfolds across such enormous timescales, these motions can persist almost indefinitely. A strange tilt acquired 4 billion years ago may still define a planet today. Earth itself has changed repeatedly over deep time. Its rotation has gradually slowed because of tidal interactions with the Moon. Hundreds of millions of years ago, days were shorter. Dinosaurs experienced faster sunrises than we do. Far enough back, an Earth day lasted only a few hours. Even now the process continues. Tiny amounts of rotational energy transfer into the Moon's orbit over time. The Moon slowly drifts away from Earth by about 3.8 centimeters per year. Not much, admittedly, about the speed your fingernails grow. Still, over immense spans of time, small effects become enormous changes, That is one of the quiet rules of the universe. Tiny motions repeated patiently can reshape worlds, which perhaps explains why astronomy feels strangely calming at night. Space moves slowly enough to humble urgency. A planet can take billions of years to settle into its present spin. Stars live for ages beyond ordinary comprehension. Galaxies drift like glowing continents through darkness. Against that scale, human worry softens slightly around the edges. Not disappear entirely, of course. Astronomy has unfortunately not yet solved taxes, awkward emails, or the mysterious tendency of socks to vanish in laundry cycles. Science continues investigating those, but the cosmos does offer perspective. Tonight, somewhere above your roof, Earth continues rotating eastward exactly as it has throughout all of recorded human history. The stars appear to move overhead because our world spins steadily through space. Meanwhile, Venus turns backward in stubborn defiance. Uranus rolls sideways through the dark, and countless distant planets perform motions stranger still. And we, small thoughtful creatures on one rotating world among trillions, get to notice. That may be the most extraordinary part of all. Because the universe did not need observers. It would have spun and collided and tilted and evolved regardless. Yet here we are, capable of looking upward and asking questions about motions unfolding across billions of years. Why do planets spin? Why do some spin backward? Why are some tilted? Why does the solar system look orderly in some places and chaotic in others? Most things in the solar system behave with surprising cooperation. That may not sound particularly dramatic at first, especially compared to exploding stars or black holes swallowing matter, but when astronomers began carefully mapping planetary motion, one pattern stood out almost immediately. The planets orbit the Sun in nearly the same direction. Most of them rotate the same way too. Their moons often follow similar paths. Even the asteroid belt broadly shares the same overall motion. It is as though the solar system remembers something, and in a way, it does. Because all of these worlds, from tiny Mercury all the way out to distant Neptune, formed from the same enormous rotating structure billions of years ago. Their shared direction of motion is not coincidence, it is inheritance. That idea alone changed astronomy profoundly. For a long time, humans viewed the planets almost like separate wandering lights in the sky. Ancient observers watched them drift against the background stars and gave them names tied to gods, myths, and stories. Mercury raced quickly across the heavens. Mars glowed red and unsettling. Venus appeared brilliant enough to cast shadows. But nobody initially understood that these objects were all connected through a common origin. Today we know the solar system is less like a random collection of worlds and more like a family. A strange family, admittedly. One sibling is sideways, another spins backward, several are wrapped in poisonous gas, and one has storms larger than Earth. Still, they came from the same place. To understand why most planets spin the same way, we have to travel back before planets existed at all. Long before Earth had oceans, before the sun ignited, before anything familiar appeared in the sky. At that point, there was no solar system, only a cold molecular cloud drifting through part of the Milky Way galaxy. An enormous region of gas and dust spread across trillions upon trillions of kilometers, mostly hydrogen, tiny traces of heavier elements, frozen particles, dark regions where starlight barely penetrated. It would not have looked dramatic from the outside. No glowing planets, no shining sun. Just a diffuse cloud hanging quietly in space. And yet hidden inside that cloud was everything that would eventually become Earth. The oceans, mountains, forests, your own body, the device playing this audio, and every planet turning slowly around the sun tonight. That thought alone is difficult to fully absorb. Every atom in your bones was once part of an interstellar cloud. Then gravity entered the story. Gravity is patient. That may be its defining characteristic. Unlike explosions or impacts, gravity rarely rushes. It pulls steadily, endlessly, gradually shaping enormous structures over immense spans of time. Some event likely disturbed the cloud. Perhaps a nearby supernova shockwave rippled through the region. Maybe neighbouring stars influenced it gravitationally. Whatever the trigger, denser pockets began collapsing inward. As the cloud contracted, something crucial happened. It started spinning faster. This effect appears everywhere in nature because of one of the most important conservation laws in physics, angular momentum. Now, angular momentum sounds like the sort of phrase designed specifically to frighten sleepy students in physics classrooms, but the concept itself is surprisingly intuitive. Imagine an ice skater spinning slowly with their arms extended outward. When they pull their arms inward, they rotate faster automatically. They are not magically generating extra energy. Instead, their existing rotational motion becomes concentrated into a smaller area. The same thing happens when enormous gas clouds collapse. Even if the original cloud rotated only slightly, and almost everything in space rotates at least a little, shrinking inward increases rotational speed dramatically. Over time, the collapsing material flattens into a spinning disk. This structure is called a protoplanetary disk, and nearly everything in the future solar system formed inside it. The Sun emerged at the centre where most material accumulated. Temperatures climbed, pressure increased. Eventually hydrogen fusion ignited, and our star began shining. Around it, the remaining disk continued spinning. Within that rotating disk, dust grains started colliding. At first, the particles were microscopic, tiny silicate grains drifting through gas, but static electricity and collisions allowed them to stick together. Small clumps formed. Those clumps hit other clumps. Pebbles became rocks. Rocks became kilometre-wide bodies called planetesimals. Once objects became large enough, gravity accelerated the process enormously. Now collisions mattered. Bodies smashed together constantly in the young solar system. Sometimes they shattered apart. Sometimes they merged. Gradually, over millions of years, larger worlds emerged from the chaos. And because all this material originated in the same rotating disk, most planets inherited the same direction of motion. That is why Earth spins eastward, why Jupiter spins eastward, why Saturn, Neptune and Mars do too. They are all following the original rotational direction of the ancient protoplanetary disk from which they formed. You can still see this pattern throughout the solar system today. If viewed from above Earth's North Pole, most planets orbit the Sun counterclockwise. Most major moons orbit their planets the same way. Most planetary rotations follow suit. Astronomers sometimes refer to this shared motion as prograde rotation. Retrograde rotation, like Venus exhibits, is the exception rather than the rule, and exceptions are often the interesting part of science. Still, before we get to the troublemakers, it's worth appreciating how extraordinary this overall alignment actually is. The solar system is enormous. Neptune orbits roughly 4.5 billion kilometers from the Sun. Countless asteroids and icy bodies drift through distant regions. Yet despite these immense scales, most objects still preserve the memory of that original spinning disk. The solar system behaves almost like a gigantic rotating fossil. Its present motion reflects ancient conditions billions of years old. There is something oddly comforting about that continuity. A motion established before Earth even existed still carries worlds through space today. Of course, the early solar system was not calm. Far from it. Young planetary systems are violent places. Modern telescopes observing newborn stars reveal swirling disks filled with turbulence, collisions, and migrating planets. Giant worlds can move inward toward their stars. Smaller bodies scatter outward. Gravitational interactions destabilize orbits constantly. Our own solar system almost certainly experienced similar chaos. During those early eras, newly forming planets collided repeatedly. Some impacts were relatively minor, others melted entire worlds. The young Earth likely resembled a glowing hellscape more than the blue planet we know today. Vast magma oceans covered much of its surface. Asteroids bombarded it relentlessly. Volcanoes erupted continuously. The moon-forming impact alone released more energy than humanity could meaningfully imagine. And yet through all that violence, the overall rotational direction of the solar system survived. That persistence tells us something important. The original angular momentum of the protoplanetary disk was enormous. Even catastrophic impacts could alter individual planets without completely disrupting the broader system's shared motion. There's an interesting everyday comparison here. Imagine stirring cream into coffee. Once the liquid begins rotating, small disturbances appear throughout the cup. Tiny whirlpools form, droplets splash, turbulence develops. But the overall swirling direction usually remains consistent. The solar system worked similarly, though admittedly on a scale involving planets instead of breakfast beverages. The reason angular momentum matters so much in astronomy is because nature is extremely reluctant to get rid of it. Once something begins rotating in space, it tends to keep rotating unless acted upon by another force. Earth has been spinning for over 4 billion years. Jupiter rotates incredibly quickly, completing one rotation in under 10 hours, despite being large enough to fit more than 1,300 Earths inside it. In fact, Jupiter spins so fast that its shape visibly bulges outward around the equator. Saturn does this too. Both planets are slightly flattened because rapid rotation pushes material outward. That outward effect is called centrifugal force, though physicists sometimes become wonderfully argumentative about the terminology involved. Scientists, despite appearances, occasionally enjoy debating details with the intensity of sports fans discussing referees. In any case, rapid planetary rotation produces noticeable physical consequences. Earth itself bulges slightly around the equator due to spin. If our planet stopped rotating entirely, oceans would redistribute dramatically. Days and nights would each last 6 months. Atmospheric circulation would change catastrophically. Fortunately, Earth shows no immediate signs of doing this, which is reassuring. Still, planetary rotation does gradually evolve over time. Earth's spin is actually slowing. Very slowly, admittedly. You need geological timescales to notice meaningfully. But tidal interactions with the Moon transfer rotational energy away from Earth, bit by bit. Hundreds of millions of years ago, days were shorter. During the Devonian period, roughly 400 million years ago, Earth experienced about 22-hour days. Much farther back, shortly after the Moon formed, a full Earth day may have lasted only 5 or 6 hours. Imagine trying to sleep through that schedule. Sunrises would arrive with alarming frequency. The Moon itself preserves evidence of this process. Because it is tidally locked, the same lunar face always points toward Earth. That locking occurred because gravitational interactions gradually synchronized the Moon's rotation with its orbit. Many moons throughout the solar system behave similarly. Gravity loves synchronization. Over enough time, orbital systems often settle into stable patterns. Rotation slows, tilts stabilize, motion becomes predictable. But not always, because sometimes the solar system remains messy. That is one reason astronomers love studying exceptions so much. Strange rotations often reveal ancient violence hidden beneath present stability. Venus spinning backward suggests something dramatic happened there. Uranus lying sideways implies enormous impacts or gravitational disturbances. Triton, Neptune's largest moon, orbits backward around its planet, strongly suggesting it was captured from elsewhere rather than forming naturally alongside Neptune. Retrograde motion often acts like a clue left behind at a cosmic crime scene. Something disrupted the original order, and understanding that disruption helps scientists reconstruct planetary history. There is another subtle point here too. Most planets not only spin in the same direction, but they also orbit close to the same plane. The planets are not scattered randomly around the Sun in every direction. Instead, their orbits mostly align within a relatively thin flat region called the ecliptic plane. Again, this traces directly back to the rotating protoplanetary disk. Disks naturally flatten as particles collide and settle into stable orbits. Similar structures appear throughout the universe. Spiral galaxies flatten into rotating disks. Rings form around giant planets. Accretion disks swirl around black holes. Rotation creates order. That may be one of the universe's most consistent habits. Take something enormous, let gravity collapse it, conserve angular momentum, and a rotating disk often appears. Within those disks, structure emerges. Stars form, planets form, moons form. Sometimes even life appears on one small spinning world, orbiting an average star in an ordinary galactic suburb. And eventually that life begins asking questions about why planets rotate at all. Which is rather lovely when you think about it. The atoms inside your brain were shaped by ancient stellar processes. Those atoms became part of Earth. Itself formed from a rotating protoplanetary disk. Earth spins because the cloud that created it spun. And now, creatures standing on that spinning world can investigate the history of the motion itself. The universe occasionally produces remarkable loops like that. Modern astronomy has given us extraordinary evidence supporting this formation model. Powerful telescopes like ALMA, the Atacama Large Millimeter Array in Chile, have directly observed protoplanetary disks around young stars. These disks often show striking ring structures where planets may already be forming. Some resemble giant cosmic vinyl records suspended in darkness. Others display gaps carved by newborn planets orbiting within them. For centuries, planetary formation remained largely theoretical. Humans understood the mathematics but could not actually watch the process happen elsewhere. Now, we can. That shift still feels astonishing. We are living during the first era in history when humanity can observe other solar systems being born. And what we see strongly confirms the broader story. Rotating disks create rotating worlds. Most inherit the same overall motion because they formed from the same spinning structure. Simple in principle, wildly complicated in practice. Because once planets become large enough, gravity begins creating all sorts of additional chaos. Large worlds perturb smaller ones. Resonances develop between orbits. Migration shifts planets inward and outward. Collisions alter rotations unpredictably. Think of it less like a perfect clock and more like an extremely crowded ice rink where everyone is carrying tremendous momentum and occasionally crashing into one another at catastrophic speeds. Order exists, but so does chaos. And over billions of years, both shape planetary systems together. Even our seemingly stable solar system may once have looked dramatically different. Some models suggest Jupiter migrated inward toward the Sun before moving outward again. Neptune likely shifted position significantly. Entire populations of smaller bodies were scattered across space. Certain early planets may have been ejected from the solar system completely. Imagine that for a moment. Worlds larger than Earth possibly thrown into interstellar darkness forever, because gravity turned slightly chaotic during the solar system's youth. Astronomy can become surprisingly ruthless. Yet despite all that instability, the dominant rotational pattern survived. Most planets still spin the same way because most inherited their motion from the original rotating disk. That ancient direction remains encoded in the solar system, like a memory too large to erase completely. The exceptions, though, are where the story becomes even more interesting. Because once scientists understood why most planets rotate normally, attention naturally shifted toward the worlds that did not. What exactly happened to Venus? How does a planet end up rotating backward so slowly that its day lasts longer than its year? And perhaps even stranger, why does Uranus appear to have tipped over almost entirely sideways like a giant frozen marble knocked askew long ago? Long before there were planets spinning through darkness, before moons orbited quietly around distant worlds, before Earth had oceans or mountains or even a solid surface, there was only a cloud, Not a cloud in the ordinary earthly sense, of course. Nothing soft and white drifting across a blue afternoon sky. This was something vastly larger and colder, an enormous molecular cloud suspended inside one quiet region of the Milky Way galaxy, a diffuse gathering of gas and dust stretching across distances so immense that human language starts becoming slightly inadequate. Inside that cloud, the future solar system existed only as scattered ingredients. Hydrogen drifted lazily through darkness. Tiny grains of carbon and silicates floated between colder regions of gas. Frozen compounds clung to microscopic dust particles. There were no planets yet, no sunlight, no familiar sky, just matter waiting. That may be one of the strangest truths in astronomy. Everything around us began as something astonishingly unremarkable. The chair beneath you, the oceans on Earth, the iron in your blood, the moon overhead, even Jupiter itself, all once existed as part of a cold, drifting cloud, almost empty by earthly standards. Space clouds are deceptive that way. They can contain enormous amounts of material while still being incredibly sparse. Even dense molecular clouds would feel emptier than the best vacuum chambers humans can build on Earth. If you somehow floated inside one without protective equipment, which would admittedly create several immediate health concerns, you might barely notice it visually at all. Yet over millions of years, gravity notices everything. Gravity is almost absurdly persistent. It never sleeps, never loses focus, never gets distracted halfway through a task, and suddenly remembers an embarrassing conversation from 6 years ago, the way humans occasionally do at 2 a.m. Gravity simply pulls. Slowly, patiently, forever. Inside the giant molecular cloud that birthed our solar system, tiny variations in density naturally appeared. Some regions contained slightly more matter than others. Those denser regions exerted slightly stronger gravitational attraction, which pulled in more matter, which increased gravity further, which pulled in still more matter. A feedback loop began. Astronomers think some outside event may have accelerated this process. Perhaps a nearby supernova exploded, sending shockwaves rippling through the cloud. Massive stars often live fast and die violently, scattering heavy elements across interstellar space when they explode. Those shockwaves can compress nearby gas clouds, triggering collapse. If that happened here, then ironically the death of one star may have helped create ours. That idea feels strangely fitting somehow. The universe recycles constantly. Stars die, their materials spread outward. New stars form from the debris. Planets emerge around those stars. Eventually life appears on at least one of those planets and begins wondering where everything came from. Astronomy is filled with cycles like that. As the cloud collapsed inward, it did not fall straight toward the center uniformly. Almost nothing in nature works with that kind of perfect symmetry. Tiny motions already existed inside the cloud. Slight drifts, gentle turbulence, random directional movement among particles, and once collapse began, those tiny motions became critically important. Because angular momentum must be conserved, that principle governs an enormous amount of cosmic behavior. If you have ever watched a spinning office chair accelerate when someone pulls their arms inward, you've seen angular momentum conservation in action. Shrinking rotating systems spin faster. The collapsing molecular cloud behaved the same way. As gravity pulled material inward, the entire cloud began rotating faster and faster, not because extra motion appeared from nowhere, but because existing motion became concentrated into a smaller space. Eventually, the growing spin produced another important effect: flattening. Matter falling inward could still move vertically at first, but collisions between particles gradually cancelled out upward and downward motion. Over time, most material settled into a broad rotating disk around the forming centre. This structure became the protoplanetary disk, and almost every major feature of the modern solar system traces back to it. The Sun formed at the centre where pressure and density climbed highest. Around it, the rotating disk spread outward for billions of kilometres. Inside that disk lay the future. Mercury existed there as dust. Earth existed there as microscopic grains. Saturn's rings existed there as drifting particles. The future moon floated invisibly among countless other fragments. There is something deeply strange about that idea. At one point in history, the difference between Earth and ordinary dust simply did not exist yet. The atoms were there, certainly, but not the structure. Not the oceans, not the continents, not the future forests or cities or living creatures, only raw material orbiting a newborn star inside a spinning disk. And the disk itself was anything but peaceful. Temperatures near the young sun became extreme. Solar radiation blasted nearby regions. Violent collisions occurred constantly as particles slammed together at enormous speeds. Farther outward, cooler regions allowed ice to form. Water vapour froze, methane condensed, ammonia accumulated. That temperature gradient shaped the entire architecture of the solar system. Close to the sun, lighter gases struggled to remain stable. Solar radiation stripped them away. Rocky worlds formed instead: Mercury, Venus, Earth, Mars. Farther out, beyond what astronomers call the frost line, temperatures dropped low enough for ices to survive. Suddenly much more material became available for planetary formation. The giant planets emerged there. Jupiter gathered enormous quantities of hydrogen and helium before the solar wind from the young sun cleared remaining gas from the disk. Saturn followed. Uranus and Neptune formed farther outward in colder regions filled with icy compounds. That single rotating cloud ultimately produced worlds radically different from one another. A scorched, metal-rich Mercury, a toxic, backward-spinning Venus, an ocean-covered Earth, a dusty frozen Mars, gas giants wrapped in storms, ice giants tilted into bizarre orientations, tiny icy bodies drifting beyond Neptune in permanent darkness, all from one cloud. The scale of transformation involved is difficult to overstate. Imagine grinding entire mountain ranges into microscopic dust, scattering them across interstellar space, then allowing gravity billions of years to slowly reassemble that material into planets. That still undersells the process. Modern telescopes now allow astronomers to observe similar disks forming around young stars throughout the galaxy. This remains one of the great scientific achievements of recent decades. For most of human history, planetary formation existed entirely in the realm of theory. Astronomers could calculate how stars and planets ought to form, but they could not directly watch the process unfold elsewhere. Now they can. Powerful observatories like ALMA peer into stellar nurseries where young stars sit surrounded by rotating disks of gas and dust. Some images reveal striking dark gaps where newborn planets may already be carving paths through the disk. Others show spirals, asymmetries, turbulence, and collisions. The universe appears to build planetary systems everywhere, and those systems often look messy. That is important because humans sometimes imagine cosmic formation as smooth and elegant, perhaps because astronomy books tend to compress millions of years into tidy diagrams. Reality appears considerably rougher. The early solar system was chaotic. Objects collided constantly. Some growing worlds shattered apart. Others merged. Asteroids crashed into protoplanets with enough force to melt crusts entirely. The young Earth itself may have been struck repeatedly by bodies large enough to sterilize entire surfaces, and throughout all this violence, the protoplanetary disk kept rotating. That shared rotational direction explains why most planets still orbit and spin the same way today. They inherited their motion from the giant cloud that started everything. The original spin never vanished. It evolved. One useful comparison is a potter shaping clay on a spinning wheel. Once the wheel rotates, everything placed onto it naturally shares the same general direction of motion. The clay can deform into different shapes. Parts may bulge outward. Sections may collapse or distort, but the underlying rotational motion remains. The solar system behaves similarly. The disk established the basic rotational pattern first. Later events modified individual worlds. That is why astronomers become so interested in exceptions. If nearly every planet inherited the same rotational direction, then worlds that behave differently must have experienced something unusual later on. Retrograde rotation is not random. Extreme tilts are not random, they are clues. Venus rotating backward suggests major disruption. Uranus lying sideways implies catastrophic impacts or gravitational interactions. Triton orbiting Neptune backward hints that it originated elsewhere entirely before being captured. The ordinary rotation of most planets actually makes the strange ones easier to investigate. Without the shared protoplanetary disk, astronomers would lack a baseline expectation. There is another fascinating consequence of the solar system's rotating origin too. Nearly everything orbits within roughly the same plane. The planets are not scattered randomly above and below the Sun like bees around a lantern. Instead, their orbits mostly align within a relatively thin flat region called the ecliptic plane. Again, this traces directly back to the flattening of the original disk. Disks naturally produce aligned orbital systems. You can observe similar patterns throughout the universe. Spiral galaxies flatten into rotating disks filled with stars. Black holes develop accretion disks around them. Saturn's rings form a flattened rotating structure. Rotation creates organization. Without angular momentum, the solar system might have looked entirely different. Planets could have orbited in wildly random directions. Stable climates might never have emerged. Orbital interactions would become far more chaotic. Instead, the giant cloud established order before planets even existed, though admittedly not perfect order. Because even within the rotating disk, local conditions varied enormously. Near the forming Sun, temperatures reached thousands of degrees. Metals and rocky compounds survived there while lighter materials evaporated. Farther outward, colder regions preserved ice and gases. Solar wind from the newborn Sun blasted through the disk too. Young stars are remarkably active compared to mature stars like today's Sun. They flare violently, emit strong radiation, produce intense stellar winds. The early Sun probably looked terrifying, not warm and comforting, more like an unstable cosmic furnace hurling energy across the forming solar system. And yet from that environment emerged Earth. That point still feels quietly miraculous. Our planet formed during an era of collisions so violent, entire worlds melted repeatedly. Asteroids bombarded the inner solar system relentlessly. The Moon itself formed from a colossal impact likely involving a Mars-sized object. Early Earth may have resembled a glowing magma ocean beneath toxic skies. Nothing about it suggested future forests or oceans or sleepy people listening to astronomy videos late at night. Yet the ingredients for all those things already existed. Carbon drifted through the disk. Water ice accumulated farther outward. Heavy elements forged inside long-dead stars became part of the forming planets. Everything necessary for future life scattered quietly through the rotating cloud long before biology appeared. The more astronomy advances, the more interconnected everything becomes. Human bodies contain atoms forged inside ancient stars. Earth's water may partly trace back to icy bodies from the outer solar system. The Moon formed from planetary debris, and all of it began within one rotating molecular cloud collapsing under gravity billions of years ago. Even now, the solar system still preserves memory of that origin. Planetary orbits continue reflecting the original disk's rotation. Asteroids largely follow similar directions. Comets from distant regions preserve material older than Earth itself. In some sense, the solar system never entirely forgot where it came from. There is also something calming about the slowness of all this. Modern life often feels compressed into notifications, schedules, deadlines, and clocks constantly measuring passing minutes. Astronomy operates differently. Clouds collapse over millions of years. Stars form slowly. Planets grow, gradually through endless collisions. Orbits evolve patiently. Gravity does not rush. A rotating cloud can spend immense stretches of time becoming a solar system, and eventually, after billions of years, creatures living on one small rocky planet may finally understand that their world still spins because an ancient cloud once turned slowly in darkness. That realization changes how ordinary motion feels. Earth rotating beneath your feet tonight is not some isolated event happening independently in the present moment. It is connected directly to processes older than oceans, older than mountains, older than life itself. The sunrise tomorrow morning will occur because of motion inherited from a collapsing cloud that existed before the sun fully formed. In a way, every dawn still carries momentum from the birth of the solar system. If the early solar system had been peaceful, most planets would probably look far more ordinary today. They would spin neatly in the same direction. Their axes might stand upright with tidy predictability. Orbits would remain calm and circular. Astronomers would have fewer headaches, fewer mysteries, and probably fewer opportunities to dramatically gesture at computer simulations during conferences. But the young solar system was not peaceful. It was violent in a way that is difficult for the human mind to comfortably picture. Not dramatic in the fast, explosive style movies often prefer, where planets shatter instantly and brilliant fireballs accompanied by orchestral music. Real cosmic violence unfolds differently, slower, larger, stranger. Worlds collided over spans of millions of years. Entire planets struck one another with energies so enormous that rock temporarily behaved like liquid. Oceans of magma spread across surfaces. Atmospheres vanished into space. Debris clouds wrapped around young worlds like glowing scars. And out of all this destruction came the modern solar system. That may be one of the most important things to understand about planets. Stable worlds are often survivors of ancient catastrophes, Earth included. Tonight our planet feels dependable beneath your feet. Oceans move with familiar tides. The moon hangs calmly overhead. Sunrises arrive reliably. The ground appears steady and ancient. But early Earth was something else entirely. A newborn world forming inside chaos. At first, planets did not emerge fully assembled. There was no moment where gravity politely announced, "Excellent, this one is now complete." Planetary formation was messy from beginning to end. Inside the protoplanetary disk, countless bodies orbited the young sun simultaneously. Tiny dust grains became rocks. Rocks became planetesimals. Planetesimals merged into larger protoplanets. Each stage involved collisions. Some impacts were gentle enough for objects to stick together. Others were not gentle at all. Imagine two mountains smashing together at tens of thousands of kilometers per hour. Now imagine both mountains are the size of continents. That begins approaching the scale involved. Astronomers sometimes describe planetary formation as a process of accretion, which sounds wonderfully calm and organized, almost like carefully stacking building blocks. In reality, it resembled a cosmic demolition derby, where gravity kept forcing contestants back onto the track. Every growing planet altered the gravitational environment around it. As worlds became larger, their gravity pulled smaller objects inward more efficiently. That increased collision rates further, and because space is enormous, impacts happened at extraordinary speeds. On Earth, objects falling through the atmosphere experience air resistance. Space offers no such courtesy. Asteroids and protoplanets accelerated freely through vacuum. When collisions occurred, the energy release became immense. Even relatively small impacts could reshape planetary surfaces. Large impacts changed everything. The moon itself likely formed this way. This remains one of the most astonishing scientific conclusions modern astronomy has reached. Our calm, familiar moon, the object humans have written poems about for thousands of years, probably originated from one of the most violent events in Earth's history. The leading explanation is called the giant impact hypothesis. According to this model, roughly 4.5 billion years ago, the young Earth collided with a protoplanet about the size of Mars. Astronomers named this hypothetical world Theia, after a titan from Greek mythology, associated with brightness and celestial light. The collision was unimaginably powerful, not a glancing bump, not an asteroid strike like the one that ended the dinosaurs, something far larger. The impact likely vaporized enormous portions of both worlds instantly. Rock melted. Debris blasted outward into orbit around Earth. Temperatures climbed so high that parts of the planet may briefly have become oceans of molten stone beneath glowing skies. And yet from that catastrophe came the Moon. Over time, the debris orbiting Earth gradually clumped together through gravity. Smaller fragments merged into larger bodies. Eventually, one dominant object formed. Our Moon was born from planetary wreckage. There is something oddly beautiful about that. The familiar object hanging above Earth tonight may literally be the surviving remains of an ancient world destroyed billions of years ago. And importantly for our story, that impact also changed Earth's rotation. Collisions do not merely damage planets, they alter motion. Imagine spinning a basketball on your finger. Now strike it sharply from the side. The spin changes immediately. Depending on the angle and force involved, the ball may tilt, wobble, speed up, slow down, or reverse direction entirely. Young planets behaved similarly, except instead of basketballs, these were worlds thousands of kilometers wide colliding at catastrophic speeds. One major impact could permanently redefine a planet's future rotation. Scientists suspect many strange planetary behaviors trace back to exactly this kind of ancient violence. Uranus provides one of the clearest examples. Even among planets, Uranus looks peculiar. Most worlds rotate somewhat upright relative to their orbits. Earth tilts about 23.5 degrees, giving us seasons. Mars tilts similarly. Jupiter barely tilts at all. Uranus, however, lies almost sideways. Its axial tilt approaches 98 degrees. If Earth tilted that far, the poles would point almost directly toward the Sun during parts of the orbit. Seasons would become extreme beyond ordinary comprehension. Entire hemispheres would experience years of continuous sunlight, followed by years of darkness. On Uranus, that actually happens. Astronomers strongly suspect one or more gigantic impacts knocked Uranus sideways during the early solar system. Something enormous hit it. Perhaps multiple things, and the effects remain visible billions of years later. That idea is quietly astonishing. A collision occurring before complex life existed on Earth may still define Uranus today. Planets remember impacts for an incredibly long time. Venus may tell a similar story. As we discussed earlier, Venus rotates backward compared to most planets. Scientists still debate exactly why. One possibility involves tidal interactions with the Sun slowly altering its rotation over immense spans of time. Another possibility is far more dramatic. A colossal impact may have reversed Venus's spin entirely. If a sufficiently large object struck Venus at the right angle during planetary formation, it could theoretically flip or dramatically alter the planet's rotation. The details remain uncertain because planetary history is frustratingly difficult to reconstruct perfectly after billions of years. Ancient surfaces get erased. Atmospheres evolve. Craters disappear. Still, collisions clearly shaped much of the solar system. Mercury may have lost enormous portions of its outer layers through impacts. Mars bears colossal scars from ancient bombardment. The Moon's heavily cratered surface preserves a visible record of violent early impacts because, unlike Earth, it lacks weather and plate tectonics to erase them. In fact, one of the reasons Earth looks comparatively smooth today is because our planet is geologically active. Wind, water, volcanism, and tectonic activity constantly reshape the surface. The Moon has no such cleanup system. It keeps its scars, and those scars reveal something important. The early solar system endured an era called the Late Heavy Bombardment. Around 4 billion years ago, Enormous numbers of asteroids and comets appear to have slammed into the inner planets repeatedly. Exactly what triggered this bombardment remains debated, though planetary migration involving Jupiter and Saturn likely destabilized countless smaller bodies. Whatever the cause, it was intense. The Moon's ancient cratered regions preserve evidence of that era almost like a fossilized battlefield. Earth experienced the same bombardment too, but our active geology erased most direct traces long ago. Still, some impacts left consequences too large to remove entirely. The Moon itself remains the greatest example. There's something deeply strange about living on a world shaped by collisions so ancient and violent that ordinary intuition struggles to process them. Human history feels long to us. Ancient civilizations seem distant. Dinosaurs belong to unimaginably remote ages. Yet all of that occurred after the solar system had already largely settled down. The truly chaotic period came first. Young planets crashed together while Earth itself was still forming. And these impacts did not merely affect surfaces, they changed planetary interiors too. When giant impacts occurred, energy transferred deep into planetary structures. Entire worlds heated internally. Heavy elements sank toward cores. Lighter materials floated upward. Magnetic fields evolved. Rotation rates changed. In some cases, impacts may even have helped create conditions favourable for life later on. The Moon-forming collision likely stabilised Earth's axial tilt over long periods. Without the Moon, Earth's orientation might wobble chaotically like Mars does, producing extreme climate instability. So one catastrophic collision billions of years ago may indirectly help maintain Earth's long-term environmental stability today. Astronomy occasionally produces cause and effect chains so enormous they feel almost fictional. A destroyed protoplanet may have helped future mammals evolve. One reason collisions matter so much is because planetary systems are crowded during formation. Imagine a newly formed solar system as a busy construction site where nobody has traffic rules and everything weighs more than continents. Objects constantly cross paths. Gravity amplifies instability. Large planets perturb smaller bodies into new orbits. Resonances develop. Some worlds migrate inward or outward through the disk itself. Computer simulations of early planetary formation often look wonderfully chaotic. Protoplanets merge repeatedly. Orbits destabilize. Smaller worlds get ejected entirely from the system. In some simulations, entire Earth-sized planets are thrown permanently into interstellar space. These are called rogue planets, lonely worlds wandering between stars without suns of their own. That possibility still feels eerie. Entire planets drifting forever through darkness because ancient collisions and gravitational interactions expelled them long ago. The universe can be surprisingly unsentimental. Yet collisions also create things. Moons form, atmospheres evolve, chemical materials mix together. Water-rich asteroids may have delivered significant portions of Earth's water during early bombardment periods. Some theories suggest organic molecules essential for life arrived partly through impacts too. The same violence capable of sterilizing planets may also have seeded future biology. Nature rarely separates creation and destruction as neatly as humans prefer, and impacts continue happening even today, though far less frequently. Earth still experiences asteroid strikes constantly, though most are tiny. Small meteors burn up harmlessly in the atmosphere every night. Larger impacts occur rarely, but remain inevitable over long enough timescales. Jupiter actually protects the inner solar system to some extent, by absorbing or redirecting many dangerous objects through its enormous gravity. In 1994, humans directly observed fragments of comet Shoemaker-Levy 9 crashing into Jupiter after tidal forces tore the comet apart. The resulting explosions were enormous. Some impact scars on Jupiter grew larger than Earth itself. and that was merely a comet fragment hitting a gas giant in the modern, relatively stable solar system. Early planetary collisions were vastly more extreme. There is another important reason scientists care so much about impacts too. Rotation itself often preserves evidence of ancient collisions. A strangely tilted world hints at catastrophic past events. Rapid rotation may suggest particular formation histories. Retrograde spin points toward major disruption. Planets behave almost like historical records written in motion rather than text. If you learn how to read those motions, entire forgotten eras become visible. That is partly why astronomy feels so detective-like at times. Scientists reconstruct events no human witnessed by studying surviving clues. A tilted axis, a moon's unusual orbit, an unexpected rotation rate, an odd planetary density, all become pieces of a much larger puzzle. And the more exoplanets astronomers discover, the clearer it becomes that collisions are not unusual exceptions, they are normal, planetary. Systems throughout the galaxy probably endured similar eras of violence during formation. Giant impacts may occur routinely across the universe whenever worlds emerge around young stars. Some exoplanets may still be experiencing them now. In fact, astronomers have observed debris disks around distant stars that likely contain the aftermath of colossal collisions. Certain systems show excess infrared radiation consistent with enormous clouds of hot dust generated by impacts between planetary bodies. Elsewhere in the galaxy tonight, entire worlds may be colliding, and eventually, after enough chaos settles down, the survivors remain orbiting their stars, carrying permanent scars in their rotation, tilt, structure, and motion. Earth is one such survivor. Venus too, Uranus certainly. Even the moon overhead is essentially the preserved memory of a destroyed world. That realization changes how stable planets feel. We often imagine worlds as permanent, calm, dependable things, great solid spheres hanging quietly in space, but planets are processes as much as objects. They evolve, collide, tilt, migrate, change. Their present appearance reflects billions of years of accumulated history, and sometimes one sufficiently violent moment can alter a world forever. Among all the planets in the solar system, Venus may be the most quietly unsettling. Not the largest, not the coldest, not the most violent in obvious appearance. Jupiter dominates in sheer scale. Saturn carries its impossible rings. Neptune hurls supersonic winds through deep blue darkness. Yet Venus possesses a different kind of strangeness. The closer scientists looked at it, the more it began to feel like a world determined to break expectations one by one. At first glance, Venus seems almost comforting, bright, familiar, beautiful even. After the sun and moon, it is usually the brightest object in the sky. Humans have watched it for thousands of years. Ancient civilizations often associated it with beauty, love, fertility, or light. The Romans named it after their goddess Venus. The Greeks linked it to Aphrodite. And honestly, from Earth, the planet does look lovely. A brilliant pale beacon appearing near sunrise or sunset. Soft and luminous, almost peaceful. Which is perhaps the greatest public relations success any hostile planet has ever achieved. Because Venus is horrifying. Not dramatically horrifying in the obvious science fiction sense with exploding volcanoes every few minutes, or giant creatures stomping across lava fields. Venus is worse in a quieter, more oppressive way. The atmosphere is thick enough to crush submarines. Surface temperatures hover around 460 degrees Celsius, hot enough to melt lead. Clouds contain sulfuric acid. The air pressure at the surface is over 90 times greater than Earth's atmospheric pressure. Spacecraft sent there tend to survive briefly before being cooked and crushed into silence. Venus is what happens when a planet becomes deeply unreasonable. And then there is the rotation. That is where things become truly strange. Most planets in the solar system rotate in roughly the same direction they orbit the Sun. Viewed from above Earth's north pole, the planets generally move counterclockwise around the Sun and spin counterclockwise as well. Venus does not. Venus rotates backward. Astronomers call this retrograde rotation. Technically, the planet spins clockwise relative to most others in the solar system. If you somehow stood safely on the surface of Venus, which would currently require engineering solutions bordering on optimism, the Sun would rise in the west and set in the east. Sunrise itself would appear wrong. That detail feels strangely unsettling, even though wrong is entirely a human perspective. The universe has no preferred sunrise direction. Yet after growing up on Earth beneath eastward dawns, imagining the opposite creates a subtle sense of disorientation. Venus quietly reverses one of the most familiar motions humans experience, and it gets stranger. Venus rotates extremely slowly. One Venusian day lasts about 243 Earth days, but Venus orbits the Sun in only 225 Earth days, meaning a full rotation takes longer than a full orbit. On Venus, a day is longer than a year. There is something wonderfully absurd about that. Imagine celebrating your birthday before the Sun has even risen once. Astronomy occasionally feels like the universe experimenting with increasingly impractical calendars. Scientists spent a surprisingly long time trying to determine Venus's rotation accurately, because the planet hides beneath thick clouds. Visible light telescopes cannot see the surface directly. Early astronomers could only observe the glowing atmosphere. For centuries, Venus remained mysterious. Some people imagined jungles beneath the clouds. Others pictured oceans. Certain early science fiction stories treated Venus almost like a tropical prehistoric Earth wrapped in mist. Reality turned out considerably less welcoming. Radar observations eventually penetrated the atmosphere and revealed the truth. A scorching rocky world rotating backward with crushing atmospheric pressure and volcanic plains stretching across enormous distances. The discovery of retrograde rotation created immediate questions. Why would Venus spin opposite to most planets? After all, as we discussed earlier, the planets formed from the same rotating protoplanetary disk. Most inherited the same general direction of motion from that ancient cloud. So what happened to Venus? Astronomers still debate the answer, and that uncertainty itself is fascinating. Even now, with robotic spacecraft exploring the solar system and powerful telescopes scanning distant galaxies, Venus remains oddly difficult to fully explain. One possibility involves catastrophic impacts. Perhaps early Venus once rotated normally like Earth. Then, during the violent chaos of planetary formation, something enormous struck it. A sufficiently large collision could dramatically alter planetary rotation. Hit a spinning world at the right angle, and you can slow it, tilt it, or potentially reverse its spin altogether. Given how violent the early solar system was, this explanation seems plausible. The young planets collided constantly. Earth itself endured the moon-forming impact. Uranus may have been knocked sideways by giant collisions, so Venus suffering a major rotational disruption would fit the broader pattern. Still, there are complications. Reversing an entire planet's spin is not easy. Venus is massive, nearly Earth-sized. Changing its rotation would require extraordinary energy and very specific impact conditions. Some simulations suggest multiple impacts may have contributed rather than one single event. Others point toward a different explanation entirely: the atmosphere. Venus possesses the thickest atmosphere among the rocky planets, and that atmosphere behaves in bizarre ways. Winds high above the surface race around the planet far faster than the planet itself rotates, a phenomenon called superrotation. The upper atmosphere circles Venus in roughly 4 Earth days, despite the planet below rotating incredibly slowly. This creates complicated interactions between atmospheric tides and solar heating. Over immense timescales, those atmospheric effects may have altered Venus's spin significantly. Combined with gravitational tidal forces from the Sun, the atmosphere might gradually have slowed and reversed the planet's rotation over billions of years. In other words, Venus may not have flipped suddenly. It may have drifted backwards slowly through subtle forces operating patiently across deep time. That possibility feels strangely eerie. A whole planet gradually reversing direction over billions of years because sunlight heated its atmosphere unevenly. Astronomy often reminds us that tiny effects become enormous if given enough time. Gravity works that way, erosion works that way, even planetary rotation may work that way. There's another remarkable aspect to Venus too. Despite being Earth's closest planetary neighbour in size and composition, it evolved into something radically different. Venus and Earth are often called sister planets because they share many similarities. Their sizes are close, their masses are similar, both are rocky worlds, both likely formed from nearby regions of the protoplanetary disk. Yet, their destinies diverged completely. Earth became temperate enough for oceans and life. Venus became an inferno. That contrast deeply fascinates planetary scientists because it suggests small differences during planetary evolution can produce wildly different outcomes. One leading explanation involves runaway greenhouse heating. Venus likely once possessed significant water. Some models suggest ancient oceans may even have existed there billions of years ago. But because Venus orbits close to the Sun, temperatures rose more easily. Water vapour accumulated in the atmosphere, and water vapour is an excellent greenhouse gas. More heat trapped more water vapour. More water vapour trapped more heat. The process accelerated. Eventually oceans may have evaporated entirely. Ultraviolet radiation from the sun split water molecules apart. Hydrogen escaped into space. Carbon dioxide accumulated in enormous quantities. The atmosphere thickened catastrophically. Surface temperatures soared. The planet transformed permanently. Earth narrowly avoided this fate. That realization remains quietly unsettling. Planetary habitability appears delicate, and Venus serves as a warning written across an entire world. Yet despite all its hostility, Venus still exerts a strange fascination, partly because it remains mysterious. Its thick atmosphere hides much from direct observation. Spacecraft struggle to survive on the surface. Radar mapping revealed enormous volcanic plains, mountain ranges, and strange geological features, but many questions remain unanswered. Is Venus still volcanically active today? How exactly did its rotation evolve? Did it once possess oceans? Could microbial life perhaps have existed there long ago? Some scientists have even speculated about the possibility of microbial organisms surviving high in the cooler upper atmosphere. Though evidence remains highly controversial and uncertain, Venus continues refusing to become simple, and perhaps that is fitting for a planet that spins backward while wrapped in acid clouds beneath crushing pressure. One especially odd feature of Venusian rotation involves its relationship with Earth. Because of orbital resonances, Venus rotates in such a way that during each close approach to Earth, nearly the same side of Venus tends to face our planet. This synchronization may be coincidence amplified by gravitational interactions, or perhaps some subtle tidal relationship developed over immense timescales. Either way, it adds another layer of strange behavior to an already peculiar world. The more closely scientists examine Venus, the more it seems less like an ordinary planet, and more like a collection of unanswered questions wrapped in clouds. There's something philosophically interesting about retrograde rotation too. Humans naturally expect systems to behave consistently. We like patterns. Predictability feels comforting. Once scientists understood that most planets spin the same direction because of the original protoplanetary disk, Venus immediately stood out. It broke the pattern, and broken patterns attract attention. That tendency exists throughout science. Exceptions often matter most because they reveal missing pieces in our understanding. A planet spinning backward suggests hidden processes, ancient impacts, atmospheric evolution, gravitational interactions operating over billions of years, Venus tells astronomers the solar system was not neat, it was dynamic, chaotic, violent. The planets we see today are survivors of complicated histories rather than perfectly orderly products, and the weird worlds preserve the best clues. Imagine if Venus rotated normally. Astronomers might never investigate planetary spin evolution so deeply. Questions about atmospheric tides and rotational dynamics might receive far less attention. But because Venus behaves strangely, it forces deeper understanding. In that sense, unusual planets become scientifically valuable precisely because they refuse to cooperate. There is also something oddly humbling about the fact that an entire planet can rotate backward simply because of events occurring billions of years ago. Perhaps an impact changed everything. Perhaps atmospheric forces slowly reversed the spin. Either way, the present motion preserves ancient history. Venus still carries the consequences. That idea appears everywhere in astronomy. Modern planetary behaviour often reflects forgotten events from unimaginably distant eras. Rotations, tilts, orbital resonances, moon systems, atmospheric composition all preserve clues about formation and evolution. Planets are historical objects. Their motion is memory. Even Earth retains such memories. The moon-forming impact altered our world forever. Earth's axial tilt shapes seasons. The slowing rotation lengthens days gradually. Ancient collisions delivered water and heavy elements. Nothing in the solar system exists independently of history. Venus simply wears its history more obviously than most, and because of that, it occupies a fascinating place in human imagination. Bright enough to dominate twilight skies, hostile enough to destroy spacecraft rapidly. Familiar in size yet alien in behaviour, a world where sunrise comes backward beneath toxic clouds. There's an almost literary quality to Venus sometimes, though the science alone is strange enough without embellishment. A planet that resembles Earth from far away, but becomes deeply wrong upon closer inspection. Astronomy occasionally produces worlds like that. Places that remind us how narrow Earth's habitability really is. And Venus is especially important because it demonstrates that planetary evolution is not guaranteed to produce stability or comfort simply because a planet starts Earth-like. Small differences matter, rotation matters, atmospheres matter, distance from the sun matters, time matters enormously. Billions of years allow worlds to drift toward radically different outcomes. Venus drifted toward heat, pressure, and backward rotation. Earth drifted toward oceans and life. The reasons why remain one of planetary science's most compelling investigations. Future missions may eventually provide clearer answers. New spacecraft are planned to study Venus in greater detail. Improved radar mapping, atmospheric analysis, and perhaps even long-duration aerial probes may help scientists reconstruct the planet's history more precisely. Because despite everything we have learned, Venus still guards many secrets beneath its clouds, and among those mysteries, the backward spin remains one of the most captivating. A planet rotating opposite its neighbours suggests that the solar system's history was not merely about orderly formation from a spinning disk. It was also about disruption, catastrophe, chaos, ancient events powerful enough to change the direction of worlds. Far beyond the warmth of Earth, past the asteroid belt, beyond Jupiter's giant storms and Saturn's pale rings, there drifts a planet that seems to have suffered a very peculiar accident. Uranus does not merely spin strangely. It appears to have tipped over almost completely. Most planets rotate somewhat upright relative to the flat plane of the solar system. Earth tilts by about 23.5 degrees, which is enough to give us seasons. Mars tilts similarly. Jupiter barely tilts at all. Even Saturn, despite its dramatic rings, remains reasonably aligned. Uranus, however, lies on its side with an axial tilt of roughly 98 degrees. That number is so extreme it almost stops sounding meaningful at first. But the consequences are extraordinary. Imagine Earth gradually tipping farther and farther over until the North Pole pointed nearly toward the Sun. Day and night would begin behaving in ways almost impossible to intuit naturally. Seasons would grow bizarre. Entire hemispheres would spend vast stretches of time facing sunlight continuously, while the opposite side disappeared into prolonged darkness. On Uranus, this actually happens. For parts of its orbit, one pole points almost directly at the Sun while the other faces away. Decades pass beneath uninterrupted daylight, then decades pass in darkness. A single Uranian year lasts 84 Earth years, which means each season continues for about 21 Earth years. Imagine a winter lasting longer than many human adulthood phases. Children could be born, grow up, graduate, and move away before spring arrived. The planet behaves less like an ordinary rotating world and more like some enormous cosmic lantern rolling slowly around the Sun, and naturally astronomers wanted to know why. Because once again, Uranus breaks the pattern established by the ancient protoplanetary disk. The planets were supposed to emerge from the rotating cloud sharing roughly similar orientations. Slight variations made sense, moderate tilts made sense, but nearly sideways? That suggested something catastrophic had happened. In fact, Uranus may represent one of the clearest surviving examples of giant impacts reshaping entire worlds. The leading explanation is relatively straightforward in principle. Something enormous hit it, perhaps more than once. Early in the solar system's history, Uranus likely rotated more normally. Then during the chaotic era of planetary formation, a collision altered everything permanently. A sufficiently massive impact could tilt an entire planet dramatically. And unlike Earth or Venus, Uranus preserves the result in spectacular fashion. The planet still rolls through space sideways billions of years later. That idea is astonishing if you pause long enough to absorb it properly. A collision occurring before complex life even existed on Earth may still define Uranus today. Planetary memory operates on timescales far beyond ordinary human experience. When we think about accidents, we usually imagine temporary consequences. A broken object gets repaired. A damaged road gets rebuilt. Even major disasters eventually fade into history. But planets are different. Their scars can persist almost indefinitely. An impact during the birth of the solar system can remain visible 4 billion years later in the tilt of an entire world. And Uranus wears that ancient trauma openly. There's something oddly endearing about Uranus scientifically too. It is one of the solar system's quieter giants. Jupiter dominates with enormous storms and overwhelming scale. Saturn captures attention immediately with its rings. Neptune dazzles with deep blue colour and violent winds. Uranus often gets overlooked, which is unfortunate because it is wonderfully strange. The planet itself is classified as an ice giant rather than a gas giant, though the distinction is slightly misleading. Uranus does contain hydrogen and helium, but it also holds much larger proportions of water, ammonia and methane ices deep within its interior. The methane in its atmosphere absorbs red wavelengths of light, giving Uranus its pale blue-green colour. And because Uranus rotates sideways, even its magnetic field behaves oddly. Most planetary magnetic fields align roughly with rotational axes. Earth's magnetic field is tilted somewhat but remains reasonably centred. Uranus ignores this convention entirely. Its magnetic field is wildly tilted and offset from the planet's centre, creating one of the strangest magnetospheres in the solar system. Imagine a bar magnet shoved awkwardly through a spinning sideways planet at the wrong angle. That begins approaching the weirdness involved. As Uranus rotates, its magnetic field tumbles through space in a lopsided corkscrew motion. The result is an incredibly dynamic magnetic environment, unlike anything seen on Earth. Again, the planet behaves almost as though cosmic order partially failed there. Scientists still debate exactly what kind of collision could have produced Uranus's present tilt. One possibility involves a single enormous impact with a protoplanet roughly twice Earth's mass. Another idea suggests multiple smaller impacts gradually tipped Uranus over through repeated collisions. Some computer simulations indicate that one carefully angled giant collision could explain much of what we observe today, including the tilt and certain characteristics of the Moon system. Others suggest the situation may have been even more chaotic. That uncertainty highlights something important about planetary science. Even when astronomers know broadly what happened, reconstructing precise details billions of years later becomes extremely difficult. The solar system no longer preserves perfect records. Worlds evolve, surfaces change, debris disappears, ancient impacts erase traces of even older impacts. Scientists essentially become detectives working from surviving evidence, and Uranus presents a particularly complicated crime scene. One fascinating clue comes from its moons. Uranus possesses 27 known moons, many named after characters from Shakespeare and Alexander Pope, which gives the Uranian system a surprisingly literary atmosphere compared to the Roman mythology dominating much of the solar system. There's something delightful about moons named Oberon, Titania, Miranda, Auriel and Umbriel orbiting a sideways ice giant in deep space. Astronomy occasionally sounds less like science and more like a fantasy library. Organised by physicists, the moons themselves orbit along Uranus's tilted equatorial plane, suggesting they formed or reformed after the tilting event occurred. If Uranus had simply tipped gradually without major disruption, the Moon system might look different. Instead, the alignment hints that either the moons formed from debris after the impact or their orbits adjusted over immense timescales afterward. Miranda, one of Uranus's moons, looks especially bizarre. Voyager 2 images revealed a surface resembling mismatched geological patches stitched together from different worlds. Massive cliffs, strange ridges and chaotic terrain cover the moon. Some scientists suspect Miranda may once have been shattered apart and partially reassembled. Even Uranus's moons seem unable to escape the system's strange history. And then there are the rings. Many people forget Uranus has rings at all, because Saturn's magnificent system tends to dominate public attention. But Uranus possesses a complex ring system too, though darker and fainter. Viewed from Earth, those rings undergo dramatic orientation changes because of the planet's sideways tilt. Sometimes we see them broadside, sometimes nearly edge-on. The geometry of the Uranian system constantly shifts in unusual ways, because the whole planet effectively rolls around the Sun instead of spinning upright. If you could somehow watch Uranus over millions of years from far away, its motion might look almost unstable, as though something had knocked it off balance long ago and it never fully recovered. Yet despite appearances, Uranus remains gravitationally stable. Planets can survive extraordinary disruption. That may be one of the most surprising lessons of planetary science. Worlds are remarkably resilient. Even giant impacts do not necessarily destroy them completely. Instead, planets absorb catastrophe and continue evolving. Earth survived the moon-forming collision. Venus survived whatever altered its rotation. Uranus survived being tipped sideways. The solar system is less a collection of pristine, untouched objects and more a gallery of survivors. There's another subtle consequence of Uranus's tilt too. Its weather and atmospheric circulation become deeply unusual. Because sunlight strikes the planet so differently during its long seasons, atmospheric dynamics shift in ways still not fully understood. For years, Uranus appeared strangely calm compared to Neptune, despite both planets sharing similar compositions. Then, astronomers began observing seasonal changes and occasional storms. Even sideways worlds have weather. Though admittedly the concept of weather on an ice giant the size of Uranus stretches everyday intuition slightly. Wind speeds there can exceed hundreds of kilometers per hour. Temperatures plunge to some of the coldest in the solar system. Deep beneath the atmosphere, pressures rise enormously. And somewhere inside all that complexity, the planet keeps rotating sideways patiently around the Sun. One especially interesting possibility is that Uranus's tilt may actually have prevented even worse chaos later on. Planetary systems are highly sensitive to gravitational interactions. Slight differences early in formation can dramatically alter long-term evolution. It's possible Uranus's collision changed orbital dynamics enough to influence the broader architecture of the outer solar system. In other words, one ancient impact may have affected far more than just Uranus itself. The solar system behaves like a connected system of gravitational relationships. Change one major body significantly, and everything else adjusts too. Jupiter's gravity shapes asteroid belts. Saturn influences orbital resonances. Neptune helps sculpt distant Kuiper belt objects. Uranus's sideways orientation likely contributed subtle effects throughout billions of years of solar system evolution. Again, astronomy constantly reveals enormous consequences emerging from ancient events. There is also something psychologically interesting about how humans react to Uranus. People tend to find it amusing because of the pronunciation issue in English, which astronomers have spent decades heroically trying to survive professionally. Imagine dedicating your life to studying one of the most fascinating worlds in the solar system, while audiences continuously giggle whenever you mention it. Planetary scientists deserve more sympathy than they sometimes receive, yet beneath the unfortunate jokes lies a genuinely extraordinary world. A planet tipped sideways by ancient violence, a world where seasons last decades, a magnetic field tumbling through space at bizarre angles, moons orbiting a tilted equator around a rolling giant, and perhaps most remarkable of all, Uranus demonstrates how dramatically collisions can reshape planets without destroying them entirely. Before astronomers understood giant impacts properly, planetary systems often seemed more orderly in scientific imagination. Worlds formed neatly from disks and settled calmly into stable arrangements. Modern understanding is far messier. Collisions matter enormously. They shape rotation, tilt axes, create moons, alter atmospheres, influence climates, possibly even determine whether life becomes possible later on. Without giant impacts, Earth itself might be profoundly different. Without Uranus's impacts, the outer solar system might have evolved differently. Violence helped create the modern architecture of the planets, and because of that, the solar system preserves both order and chaos simultaneously. Most planets still orbit the same direction because of the original rotating disk, yet individual worlds display scars from later disruptions. That combination is what makes planetary science so compelling. The universe establishes broad patterns first, then reality complicates them. There's another curious aspect to Uranus too. Despite its dramatic tilt, the planet does not seem emotionally bothered by any of this, if one may briefly anthropomorphize an ice giant. It simply continues, sideways, cold, rolling around the sun every 84 years beneath pale sunlight. That persistence feels oddly comforting in its own way. Planets endure, catastrophes happen, impacts occur, systems destabilize, entire worlds get knocked over, and still the survivors keep orbiting, keep rotating, keep existing beneath distant stars. Tonight, while Earth spins normally beneath familiar skies, Uranus continues its sideways journey billions of kilometers away. One pole currently leans toward darkness, while the other drifts through sunlight. Its moons circle along impossible angles. Its magnetic field tumbles through space like a confused compass, and all of it likely traces back to ancient collisions from the violent youth of the solar system. Which raises another important question. What exactly does wrong way even mean in astronomy? The phrase wrong way sounds simple until astronomy gets involved. At first glance, it feels obvious enough. Most planets spin one direction. A few spin the opposite way. Therefore, those planets must be rotating incorrectly somehow. Except the universe does not really recognize correct and incorrect in the way humans prefer. Space has no up or down. No cosmic left or right, no universal sunrise standard carefully enforced by celestial authorities. There is no giant sign floating above the solar system declaring planets must rotate this direction only. Instead, astronomers use reference frames and conventions, and once you start examining those conventions closely, planetary rotation becomes much stranger and more interesting than everyday language suggests. The term retrograde rotation simply means that a planet rotates opposite the direction expected based on the broader motion of the solar system. Viewed from above Earth's north pole, most planets orbit the Sun counterclockwise and rotate counterclockwise as well. That shared motion traces back to the original protoplanetary disk. Retrograde planets rotate clockwise instead. Venus is the clearest example, but even here, the situation becomes slightly complicated, because technically, astronomers could have defined north differently. This is one of those quietly amusing details in science. Many things that feel deeply fundamental turn out partly dependent on human choices. Planetary north poles are usually defined according to rotational direction using the right-hand rule. If you curl the fingers of your right hand along the direction of rotation, your thumb points toward the North Pole. Most planets therefore ended up with north poles above the solar system's general orbital plane. Venus rotates opposite the others, so its north pole effectively points downward relative to most planets. But astronomers could theoretically have labelled the opposite pole as north instead. In that case, Venus would appear to rotate normally. The planet itself would not change at all, only the naming convention would. This highlights something important about astronomy. Nature exists independently of human labels. The universe simply behaves however physics allows. Humans then construct systems to describe those behaviours consistently. Retrograde rotation is useful terminology because it identifies planets deviating from the solar system's dominant rotational pattern. But the universe itself has no emotional investment in which direction a planet spins. Still, those deviations matter scientifically because they reveal history. Most planets inherited their motion from the rotating protoplanetary disk. Therefore, objects moving differently probably experience significant disruption later on. Retrograde motion acts like evidence left behind after ancient gravitational chaos, and retrograde behaviour appears in more places than just planetary rotation. Some moons orbit backward around their planets. Certain comets travel retrograde paths around the Sun. Even galaxies can rotate differently relative to neighbouring systems. Astronomy is filled with objects refusing to cooperate with local expectations. One particularly fascinating example is Triton, Neptune's largest moon. Triton orbits Neptune backward compared to Neptune's rotation. Astronomers call this a retrograde orbit. That detail strongly suggests Triton did not originally form around Neptune at all. Instead, scientists think Triton was likely a Kuiper belt object, captured by Neptune's gravity long ago. The Moon essentially arrived from elsewhere, and never aligned properly with Neptune's original rotational system. And because Triton moves retrograde, tidal interactions gradually pull it inward toward Neptune, instead of outward like Earth's moon. Eventually, billions of years from now, Triton may spiral close enough to break apart into rings, or crash into Neptune entirely. Retrograde motion often hints at unstable histories. Another wonderful example appears among exoplanets. As astronomers began discovering planets around other stars, they expected most systems to resemble ours somewhat. Broadly orderly, roughly aligned, planets orbiting neatly within flat rotating disks. Instead, many exoplanet systems appear delightfully chaotic. Some giant planets orbit extremely close to their stars in bizarre configurations. Others possess wildly elongated orbits. Certain exoplanets even appear to orbit opposite the rotation of their stars entirely. These are called retrograde exoplanets. Imagine a giant world circling its star one direction, while the star itself spins the other way. That arrangement immediately tells astronomers something dramatic probably happened there. Perhaps gravitational interactions between giant planets destabilized the system. Maybe close stellar encounters altered orbital dynamics. Possibly entire planets migrated inward through chaotic processes early in formation. The broader point is this: retrograde motion is rarely random. It usually signals a complicated past, and that makes such worlds scientifically valuable because they preserve clues about planetary evolution. There is also something psychologically interesting about the phrase "wrong way" itself. Humans naturally interpret motion relative to familiar patterns. Earth's rotation feels normal because it is home. Sunrise in the east feels correct because it always has. Once a pattern becomes deeply familiar, deviations appear strange automatically. But from another perspective, Venus's rotation is not any more objectively wrong than Earth's. If intelligent life evolved on Venus, assuming survival beneath the crushing inferno atmosphere proved possible somehow, its inhabitants might consider westward sunrise perfectly ordinary. They would likely find Earth bizarre instead. Imagine a planet where the sun rises in the east, Venusian astronomers might say with concern. Normality depends heavily on perspective. Astronomy teaches this lesson repeatedly. Earth feels stationary until you learn it spins. The sun feels central until you learn it is one ordinary star among hundreds of billions. Human timescales feel large until you encounter stellar evolution. Retrograde rotation belongs to this category too. It feels unusual primarily because humans evolved within one particular planetary system, containing one dominant rotational pattern. Elsewhere in the universe, other arrangements surely exist, perhaps many of them. One reason astronomers care deeply about rotation is because it affects planetary behavior profoundly. Rotation influences weather, climate, magnetic fields, atmospheric circulation, even potential habitability. Earth's relatively rapid rotation helps shape global wind patterns and ocean currents. The Coriolis effect produced by rotation influences hurricanes, jet streams, and large-scale atmospheric motion. A slower rotating Earth would behave very differently climatically. Venus provides a dramatic example. Its extremely slow retrograde rotation contributes to bizarre atmospheric dynamics. Despite rotating sluggishly, the upper atmosphere races around the planet rapidly in superrotation. Winds circle Venus in only a few days, while the planet itself takes 243 Earth days to complete one spin. The atmosphere effectively outruns the planet. Again, Venus refuses to behave sensibly. Uranus's sideways rotation produces equally strange seasonal behavior. Neptune's moon Triton likely experiences complex tidal evolution because of retrograde orbiting. Rotation matters enormously. Even stars rotate. The Sun spins approximately once every 27 Earth days near its equator, though because it consists mostly of plasma rather than solid material, different latitudes rotate at different speeds. This differential rotation helps drive solar magnetic activity in sunspot cycles. Some stars rotate astonishingly quickly, others rotate slowly. Certain stars likely acquired unusual rotation rates through collisions or close interactions with companion stars. The universe seems deeply fond of spinning things. Galaxies rotate, stars rotate, planets rotate, moons rotate, black holes rotate, even giant clouds collapse into rotating disks during formation. Angular momentum conservation appears almost everywhere. And because rotation is so fundamental, changes to it often reveal important physical processes. There's another subtle point hidden inside retrograde motion too. It reminds us that the solar system was never perfectly stable. Sometimes textbooks unintentionally create the impression that planets formed neatly and remained mostly unchanged afterward. Reality was far more dynamic. Young planetary systems are chaotic environments. Worlds migrate, collide, tilt, capture moons, scatter debris, change orbits. retrograde objects preserve evidence of those ancient instabilities. In a way, they act almost like geological fault lines revealing past earthquakes. Venus spinning backward hints at major disruption. Triton orbiting backward hints at capture. Retrograde exoplanets hint at violent gravitational histories. The strange motions expose hidden events. Astronomers also distinguish between rotation and revolution carefully. Rotation refers to an object spinning around its own axis. Revolution refers to orbiting another object. Earth rotates once, roughly every 24 hours, while revolving around the Sun once every year. Retrograde behavior can apply to either motion depending on context. A planet may rotate retrograde while still orbiting normally, like Venus, or a moon may orbit retrograde around a planet, like Triton. These distinctions matter because they often point toward different formation mechanisms. Retrograde planetary rotation might result from impacts or tidal evolution. Retrograde moon orbits often suggest gravitational capture. The details become scientifically revealing. One wonderfully strange consequence of retrograde rotation involves solar motion across the sky. On Earth, the Sun appears to rise in the east because Earth rotates eastward. On Venus, the opposite occurs. Imagine growing up on a world where sunset and sunrise happened backward relative to human expectation. Your language, culture, architecture, navigation systems, and mythology would all develop differently around that basic motion. Even concepts of direction might evolve differently. Human civilization is deeply shaped by Earth's rotation in ways people rarely notice consciously. Day and night cycles influence biology, clocks, agriculture, navigation, religion, sleep itself. Planetary motion quietly structures experience. That is partly why retrograde worlds feel so fascinating. They remind us that even fundamental aspects of ordinary life depend on planetary circumstances. A different rotation produces a different sky. There is also a curious asymmetry in how humans emotionally interpret backward motion. Retrograde often sounds negative somehow, reversed, incorrect, broken. Perhaps because human minds associate forward movement with progress naturally. But in astronomy, retrograde simply means different. Physics does not care about human directional preferences. A planet rotating backward obeys gravity and conservation laws just as faithfully as any other world. The universe remains entirely indifferent to which way dawn arrives, and that indifference can feel oddly calming sometimes. Nature is not trying to create tidy systems optimized for human expectations. It simply follows physical laws wherever they lead. Sometimes that produces orderly planetary families. Sometimes it produces worlds rolling sideways beneath decades-long seasons. Sometimes it produces planets where sunrise comes backward through acid clouds. The diversity itself becomes part of the beauty. Modern exoplanet discoveries reinforce this constantly. The more planetary systems astronomers discover, the clearer it becomes that our solar system represents only one arrangement among many possible outcomes. Some systems contain hot Jupiters, orbiting scorchingly close to their stars. Others feature planets packed tightly together in resonant chains. Some worlds may wander rogue through interstellar space entirely alone, and somewhere out there countless retrograde planets almost certainly spin beneath alien skies. Perhaps some rotate so slowly that weather systems persist for centuries. Others may spin rapidly enough to flatten dramatically at the equator. Some might have multiple suns rising and setting unpredictably across their atmospheres. The universe appears remarkably creative when building planets, which perhaps explains why astronomers increasingly focus less on finding worlds identical to Earth and more on understanding planetary diversity itself. Every strange world teaches something new. Retrograde motion teaches us about impacts, tidal forces, orbital capture, migration, and gravitational instability. It reminds us that planetary systems evolve. They are not frozen mechanical diagrams. They are dynamic histories unfolding across billions of years. Tonight Earth continues spinning eastward beneath familiar stars. Sunrise tomorrow will arrive exactly where generations before us expected it. Meanwhile, Venus rotates backwards slowly through toxic clouds. Triton circles Neptune in reverse. Distant exoplanets orbit their stars along impossible trajectories, and all of them follow the same physical laws despite behaving so differently. The solar system began with shared motion, inherited from one rotating cloud. But time, gravity, and chaos complicated the story afterward, and nowhere did those complications become more dramatic than during the era when planets themselves migrated through the solar system, destabilizing entire regions and reshaping countless smaller worlds along the way. Planets are not the only things in the solar system with strange ideas about motion. Their moons can become just as rebellious. At first glance, moons seem relatively straightforward. A planet forms, smaller bodies gather around it, gravity pulls everything into orderly orbits, and eventually stable systems emerge. Simple enough. But once astronomers began studying moons carefully, especially the outer irregular ones orbiting giant planets, the neat picture started falling apart again. Some moons orbit backward, some appear captured from elsewhere entirely. Certain moons behave so strangely they seem less like natural companions and more like cosmic hitchhikers trapped by gravity long ago. And among all these odd worlds, a few stand out as particularly important because they reveal something profound about how chaotic the young solar system truly was. Take Triton, for example. Triton is Neptune's largest moon, and it immediately breaks expectations. Most large moons orbit in the same direction their planets rotate. That makes sense because moons generally form from the same rotating material surrounding a young planet. Shared origins tend to produce shared motion. Triton ignores this completely. It orbits Neptune backward, retrograde, and not just slightly unusual backward motion either. Triton travels along a nearly circular retrograde orbit very close to Neptune, which immediately tells astronomers something dramatic must have happened. Because moons do not normally form that way. If Triton had formed naturally alongside Neptune from a rotating circumplanetary disk, it should orbit prograde like most major moons. Instead, everything about its motion suggests capture. Triton probably came from somewhere else, most likely the Kuiper Belt. Far beyond Neptune lies a vast region filled with icy bodies left over from the solar system's formation. Pluto belongs there. So do countless smaller frozen worlds drifting through darkness. Astronomers suspect Triton once existed as one of those objects before Neptune captured it gravitationally billions of years ago. That process is much harder than it sounds. Gravity alone does not easily capture objects permanently, because incoming bodies usually possess enough speed to slingshot past planets and continue onward. For a stable capture to occur, energy must be removed somehow. One leading idea suggests Triton may originally have belonged to a binary system, two icy worlds orbiting each other. When they pass near Neptune, gravitational interactions destabilized the pair. One object escaped while Triton lost energy and became trapped around Neptune permanently. Essentially, Neptune stole someone else's moon. Astronomy occasionally resembles cosmic theft on unimaginable scales. Once captured, Triton probably caused absolute chaos in Neptune's moon system. Imagine suddenly introducing a massive retrograde object into a stable planetary environment. Gravitational interactions would become catastrophic. Existing moons may have collided, been ejected, or shattered apart. Some scientists think Neptune originally possessed a moon system more similar to Uranus, before Triton arrived and disrupted everything. Again, one strange moon preserves evidence of ancient instability, and Triton itself is extraordinary even beyond its orbit. The moon is geologically active. Voyager 2 observed nitrogen geysers erupting from its frozen surface in 1989. Temperatures there plunged to around -235 degrees Celsius, making Triton one of the coldest known worlds in the solar system. Yet despite the cold, internal activity continues. The surface appears relatively young too, suggesting ongoing geological renewal. A captured moon, orbiting backward around Neptune, somehow remains active billions of years later. Triton behaves less like a passive satellite, and more like a world with its own complicated history stubbornly intact. And because its orbit is retrograde, tidal forces between Triton and Neptune behave differently than they do in systems like Earth and the Moon. Earth's moon slowly drifts outward because Earth rotates faster than the Moon orbits. Tidal interactions transfer rotational energy outward gradually. Triton does the opposite. Because it orbits backward relative to Neptune's rotation, tidal interactions drain orbital energy instead. Over immense spans of time, Triton spirals inward slowly toward Neptune. Eventually, perhaps billions of years from now, Triton may cross Neptune's Roche limit, the distance where tidal forces become strong enough to tear a moon apart. If that happens, Triton could disintegrate into a spectacular ring system around Neptune, a captured moon slowly destroying itself because it travels the wrong direction. There's something strangely tragic about that, though admittedly the timeline involved is so enormous that even the word eventually becomes almost meaningless. Elsewhere in the solar system, retrograde moons appear surprisingly often around giant planets. Jupiter possesses dozens of irregular outer moons orbiting backward. Saturn does too. Many of these small moons likely originated as captured asteroids or Kuiper belt objects rather than forming naturally around their planets. Their strange orbits preserve the chaotic leftovers of planetary formation. The giant planets acted almost like gravitational vacuum cleaners during the early solar system, capturing wandering debris whenever conditions aligned correctly. Some objects became stable moons, others collided. Still others got flung back into space entirely. Gravity does not always produce neat arrangements. One particularly odd moon is Phoebe around Saturn. Phoebe orbits retrograde and appears dramatically different from Saturn's major regular moons. Its composition resembles distant Kuiper belt objects more closely, strongly suggesting capture. In fact, material blasted off Phoebe may help feed Saturn's enormous faint outer ring, one so vast it dwarfs the visible bright rings people usually imagine when thinking about Saturn. A tiny captured moon may help create one of the largest structures in the solar system. Astronomy frequently rewards small details with enormous consequences. Then there's Miranda around Uranus. We touched on Miranda briefly earlier, but this moon deserves additional appreciation because it looks utterly bizarre. Voyager 2 images revealed enormous cliffs, fractured terrain, and giant mismatched regions stitched together across its surface. Some cliffs tower over 20 kilometers high, among the tallest known in the solar system. Miranda appears almost broken. One theory suggests the moon was shattered apart by impacts long ago and then partially reassembled under gravity. Another proposes extreme tidal heating warped and disrupted the crust repeatedly. Either explanation feels wonderfully dramatic, and because Uranus itself suffered catastrophic tilting events, its moons likely endured chaotic histories too. The entire Uranian system carries an atmosphere of ancient instability. Even Earth's moon breaks expectations slightly when viewed closely. Unlike many large moons around giant planets, our moon is unusually large relative to Earth. Most planet-moon systems feature tiny satellites orbiting dominant worlds. The Earth-Moon system behaves more like a double planet pair in some respects, and its origin almost certainly traces back to giant impacts rather than ordinary moon formation. Without the collision involving Theia, Earth might never have acquired such a large companion. Again, catastrophe created something beautiful. The moon stabilizes Earth's axial tilt too, helping maintain relatively stable long-term climate cycles. Without it, Earth's orientation might wobble chaotically over geological time. Mars may illustrate this problem. The red planet lacks a large stabilizing moon, and its axial tilt appears to vary dramatically over immense timescales. Climate conditions likely shifted wildly as a result. One ancient collision around Earth may therefore have influenced the future stability necessary for complex life. That remains one of astronomy's strangest recurring themes. Violence creates order. Collisions destroy worlds while simultaneously building moons, stabilizing climates, redistributing water, and reshaping planetary evolution. The solar system's present calm emerged from extraordinary chaos, and moons preserve much of that hidden history. Some formed naturally alongside their planets, some formed from impact debris, some were stolen gravitationally from elsewhere, some may be surviving fragments of large destroyed bodies. Each orbital pattern tells part of the story. There's also something psychologically fascinating about moons specifically. Planets often feel distant and abstract because of their immense size. Moons, however, seem more personal somehow. Perhaps because humans have always lived beside one. The moon shapes tides, calendars, myths, sleep, poetry, navigation, and cultural memory. For most of human history, it was the nearest celestial object besides the sun. So discovering that moons elsewhere can behave so strangely feels oddly intimate. Backward moons, captured moons, broken moons, frozen moons with hidden oceans, volcanic moons erupting sulfur. The solar system's satellites turned out far more diverse than anyone expected. Io, one of Jupiter's moons, is the most volcanically active world known. Europa likely hides a vast ocean beneath ice. Enceladus sprays water vapor into space from underground. Seas, Titan possesses lakes and rivers made not of water, but liquid methane and ethane. Some moons may actually offer better conditions for life than certain planets do. Again, the universe refuses simplicity. One especially intriguing category involves irregular moons. These are typically small distant moons orbiting giant planets along eccentric, highly tilted or retrograde paths. Their strange motions strongly suggest capture rather than local formation. The outer regions around Jupiter and Saturn contain swarms of such objects. In some ways, they resemble fossilized remnants of early solar system chaos. Tiny worlds trapped by gravity billions of years ago still circling giant planets today. And because they orbit far from their planets, many irregular moons experience weak gravitational binding. Some may eventually escape entirely through long-term perturbations. Nothing in celestial mechanics remains perfectly fixed forever. There's another important reason astronomers study strange moons too. They help explain planetary migration. Modern models suggest the giant planets did not form exactly where they orbit today. Jupiter, Saturn, Uranus, and Neptune likely shifted positions during the solar system's youth. Those migrations destabilized countless smaller bodies. Some objects got scattered inward, others flung outward. Some became captured moons. Retrograde and irregular satellites preserve evidence of this migratory era. Without them, reconstructing planetary migration would become far harder. Moons become historical records, and because they often lack atmospheres or active geology, many preserve ancient conditions better than planets do. The Moon still carries crater scars from the late heavy bombardment. Callisto preserves ancient surfaces largely unchanged for billions of years. Small icy moons preserve compositions tracing back to the outer solar system's formation. Planetary scientists essentially read moons like archives. There is also something emotionally calming about realizing how many worlds exist quietly beyond Earth's familiar sky. Human experience feels centered naturally around one planet and one moon. Yet the solar system contains hundreds of moons, each with unique histories and motions. Some drift backward through darkness. Some hide oceans beneath frozen crusts. Some may eventually shatter into rings. Some were stolen from distant regions long ago, and all continue orbiting patiently while Earth spins beneath ordinary human concerns. Tonight, Neptune still carries Triton backward around itself in cold darkness billions of kilometers away. Saturn's captured moons drift through tilted orbits beyond the bright rings. Uranus's shattered-looking satellites circle their sideways planet, and Earth's moon continues pulling gently at our oceans exactly as it has throughout all of recorded human history. The sky appears calm from here, but hidden inside those motions are stories of capture, destruction, migration, and ancient gravitational chaos stretching back to the birth of the solar system itself. When people imagine forces powerful enough to reshape planets, they usually think of impacts, enormous collisions, explosions, violent catastrophes, and to be fair, the early solar system certainly contained plenty of those. But there is another force just as capable of changing worlds, though it operates in a completely different way, slowly, patiently, almost invisibly. Gravity does not always need dramatic collisions to alter planetary motion. Given enough time, it can gradually rewrite the rotation of entire worlds through nothing more than persistent tidal interactions. That idea feels strange at first because gravity often seems passive in everyday life. We notice it mostly when things fall downward or when our knees complain about stairs. Yet on cosmic timescales, gravity becomes one of the greatest sculptors in the universe. Mountains rise because of it, stars form because of it, galaxies rotate because of it, and planets slowly change their spin because of it too. Earth itself is already experiencing this process right now. At this exact moment, the moon's gravity is subtly slowing Earth's rotation. Not enough for you to notice while trying to fall asleep tonight, fortunately. The effect is tiny on human timescales, but over millions and billions of years, tiny effects become transformative. This is one of astronomy's favourite tricks. The universe often accomplishes extraordinary things through persistence rather than speed. To understand how gravity alters rotation, imagine Earth without oceans for a moment. The moon would still pull on the planet gravitationally, but the effects would be much weaker and harder to notice. Oceans, however, can move. As the moon's gravity pulls on Earth, it creates tidal bulges in the oceans. One bulge forms on the side facing the moon, another on the opposite side due to differences in gravitational pull across Earth's diameter. If Earth did not rotate, those bulges would remain perfectly aligned with the moon. But Earth rotates faster than the moon orbits. Our planet completes one rotation in roughly 24 hours, while the moon takes about 27.3 days to orbit Earth. That difference matters enormously. Because Earth spins quickly, the tidal bulges get dragged slightly ahead of the moon's orbital position. The oceans essentially pull forward faster than gravity can keep perfectly aligned. Now something interesting happens. Those displaced bulges exert their own gravitational pull on the moon. The bulges tug the moon forward slightly in its orbit, and when you pull an orbiting object forward, it gains orbital energy and moves farther away. Meanwhile, Earth loses a tiny amount of rotational energy in the process. The result is beautifully strange. The moon gradually drifts away from Earth, and Earth gradually spins more slowly. This is not theory. Astronauts left reflectors on the moon during the Apollo missions, allowing scientists to bounce lasers off them and measure the moon's distance extremely precisely. The moon recedes from Earth by about 3.8 centimeters per year, roughly the speed your fingernails grow. Again, astronomy loves slow transformations. Earth's rotation slows by tiny fractions of a second over long timescales as a result. Hundreds of millions of years ago, days were noticeably shorter. During the Devonian period, around 400 million years ago, Earth likely experienced roughly 22-hour days. Much farther back, shortly after the moon formed, days may have lasted only 5 or 6 hours. Imagine trying to organise sleep schedules on such a planet. Sunrises would arrive with almost aggressive enthusiasm. Dinosaurs themselves lived beneath faster spinning skies than ours. That realisation feels oddly surreal. The length of a day, something humans often treat as permanent and fundamental, is actually temporary. Earth's rotation evolves. Given enough time, the planet changes rhythm. and this same process appears throughout the solar system. Mercury provides one of the most elegant examples. At first glance, many people assume Mercury should behave similarly to Earth, simply spinning while orbiting the Sun. Instead, Mercury exists in something called a 3-to-2 spin-orbit resonance. The planet rotates exactly 3 times for every 2 orbits around the Sun. This arrangement emerged because the Sun's gravity gradually altered Mercury's rotation over immense spans of time. Early in its history, Mercury likely rotated faster, but because it orbits so close to the Sun, solar tidal forces became extremely strong. Over billions of years, those forces slowed the planet's spin until it settled into its present resonance. Mercury essentially became gravitationally synchronized into a stable pattern. Nature enjoys synchronization remarkably much. Moons become tidally locked. Planets enter resonances. Orbital periods align. Given enough time, gravity organizes motion into repeating relationships. Our moon offers the most familiar example. It always shows the same face to Earth. People sometimes mistakenly believe the moon does not rotate at all because of this. In reality, it rotates exactly once during each orbit around Earth. The synchronization is perfect. One lunar hemisphere permanently faces us, while the far side remained unseen by humans until spacecraft finally photographed it. This state is called tidal locking, and it is incredibly common. Many moons throughout the solar system are tidally locked to their planets. Pluto and its moon Charon are mutually locked, each always showing the same face to the other. Some exoplanets orbiting very close to their stars are likely tidally locked too, with one hemisphere trapped in endless daylight while the other remains in permanent darkness. Imagine living on such a world. One side beneath eternal noon, the other under infinite night. Somewhere between them, perhaps, a narrow habitable twilight band where temperatures remain survivable. Astronomy frequently sounds like speculative fiction despite being entirely real. Venus may also owe part of its bizarre rotation to tidal effects. As we discussed earlier, Venus rotates extraordinarily slowly and backward. One possible explanation involves atmospheric tides combined with solar gravitational interactions, gradually altering the planet's spin. Over billions of years, those forces may have slowed Venus dramatically and eventually reversed its rotation, not through sudden catastrophe, but through relentless persistence. Gravity can behave almost like erosion sometimes. Tiny effects repeated endlessly become unstoppable. Even Mars experiences rotational evolution. Its 2 small moons, Phobos and Deimos, behave differently because of tidal interactions. Phobos orbits so close to Mars that it actually circles the planet faster than Mars rotates. As a result, tidal forces pull Phobos inward instead of outward. The moon slowly spirals toward Mars. Eventually, perhaps 30 to 50 million years from now, Phobos may either crash into Mars or break apart into a ring system. Another moon doomed by gravity. The solar system contains surprising amounts of slow-motion tragedy. There's something philosophically interesting about tidal evolution too. Human intuition often struggles with gradual change. We notice sudden events easily, but slow processes become almost invisible unless viewed across immense spans of time. Yet many of the universe's most powerful transformations operate this way. Stars evolve slowly. Continents drift slowly. Galaxies collide slowly. And planetary rotation changes slowly. The universe possesses extraordinary patience. Given enough time, gravity reshapes almost everything. Even Earth's future remains tied to these processes. Billions of years from now, if humanity somehow still exists, Earth's rotation will continue slowing. The moon will continue drifting outward. Total solar eclipses will eventually disappear because the moon will appear too small in the sky to fully cover the sun. Future creatures, whatever they may be, might never witness the kind of eclipses humans experience today. They exist only during a temporary window of celestial geometry. Astronomy often reveals ordinary experiences to be temporary cosmic accidents. Another fascinating example of gravity rewriting motion appears among exoplanets. Astronomers have discovered giant planets orbiting extremely close to their stars, so close that their years last only days. These hot Jupiters endure intense tidal forces. Many are probably tidally locked already. One side permanently faces the star beneath blazing heat, while the opposite side remains darker and cooler. Wind speeds there may exceed thousands of kilometers per hour, as atmospheres attempt redistributing heat between hemispheres. Gravity creates climate systems too. In some binary star systems, tidal interactions become even more extreme. Stars themselves can become tidally locked to one another, rotating in synchronization while orbiting closely together. Some stars get stretched into distorted egg-like shapes by gravitational forces from companions. Again, the universe seems deeply unwilling to leave anything perfectly untouched. Motion evolves. That is perhaps the broader lesson. Rotation is not fixed forever. Planets are not born spinning one way permanently. Moons are not guaranteed eternal stability. Gravity keeps working endlessly in the background, adjusting systems bit by bit across deep time. There's also an emotional quality to this idea that feels oddly calming. The universe is not static, not frozen. Everything changes eventually. Even motions that feel eternal are temporary arrangements evolving slowly beneath the surface. Earth's familiar 24-hour day is not some universal constant written permanently into reality. It is simply the current stage of an ongoing gravitational relationship with the Moon, and that relationship itself emerged from an ancient impact billions of years ago. The sky we know is historically specific. That realization changes how ordinary things feel. Tides become visible evidence of celestial mechanics. Moonlight becomes part of a long gravitational conversation between worlds. Even the length of a day becomes dynamic rather than fixed. Astronomy consistently transforms familiar experiences into something stranger. There's another subtle consequence of tidal evolution too. It often stabilizes systems. Tidal locking reduces chaotic rotational behavior over time. Energy dissipates. Motion synchronizes. Orbits circularize gradually. In a sense, gravity prefers order eventually. But reaching that order can take billions of years. And during those immense spans of time, all sorts of complicated intermediate states emerge. Mercury settled into resonance. The Moon became locked. Venus drifted toward bizarre, slow retrograde rotation. Phobos spirals inward toward destruction. Different systems follow different evolutionary paths depending on masses, distances, compositions, and histories. No two worlds evolve identically. That diversity becomes especially important when considering exoplanets, because tidal effects may strongly influence habitability. A tidally locked planet around a red dwarf star might still support life under certain conditions. Atmospheric circulation could transport heat effectively enough to prevent atmospheric collapse on the dark side, or perhaps oceans might redistribute warmth. Scientists are still investigating these possibilities actively, because many potentially habitable exoplanets orbit close to small stars where tidal locking becomes likely. Once again, planetary rotation turns out deeply important for understanding worlds, not merely an abstract astronomical detail. Rotation affects climate, weather, magnetic fields, temperature distribution, and potentially biology itself. The way a planet spins may help determine whether life becomes possible there. And gravity quietly controls much of that evolution over time. One of the most extraordinary things about tidal forces is that they arise simply because gravity weakens with distance. The side of Earth closer to the Moon experiences slightly stronger gravitational pull than the far side. That difference stretches the planet subtly. Tides are essentially gravity gradients made visible. The same physics stretches stars near black holes, creates volcanic heating inside moons like Io, distorts galaxies during close encounters. Tiny differences in gravitational pull across distance create enormous consequences. The universe builds complexity from surprisingly simple rules, and because gravity never stops working, tidal evolution never fully stops either. Even seemingly stable systems continue changing gradually. Perhaps that is why astronomy feels both humbling and soothing simultaneously. The cosmos operates across timescales so vast that urgency softens slightly by comparison. Planets drift, moons migrate, rotations evolve, gravity patiently rewrites motion, one tiny fraction at a time. Tonight Earth spins beneath familiar stars while the moon slowly inches outward exactly as it has for billions of years. Mercury remains locked in resonance near the Sun. Venus rotates backward through thick clouds. Distant exoplanets probably sit tidally frozen beneath alien skies. And all of it happens because gravity refuses to let motion remain unchanged forever. If you could travel backward through time and witness the solar system shortly after its birth, you probably would not recognize it. Not because the planets looked unfamiliar, though many certainly did, but because almost nothing behaved with the calm stability we associate with the modern solar system today. The current arrangement of worlds feels orderly. Mercury circles close to the Sun. Venus follows. Earth turns steadily beneath the Moon. The giant planets remain far outward where they seem permanently settled. Everything appears almost clockwork-like from the human perspective. But early on, the solar system was unstable in ways bordering on alarming. Planets migrated, asteroids scattered everywhere. Entire regions underwent gravitational upheaval. Massive collisions reshaped worlds repeatedly. And somewhere, during all that chaos, many of the strange rotations and tilted planets we observe today acquired their present behaviour. The modern solar system is less like a pristine, untouched machine, and more like the surviving aftermath of an ancient cosmic riot. That realization emerged gradually. For a long time, astronomers assumed planets probably formed roughly where they orbit today. The solar system seemed so regular that large-scale planetary migration felt unnecessary. Then scientists started running detailed computer simulations, and the simulations produced problems. Specifically, the outer solar system did not behave correctly unless the giant planets moved significantly during their early history. This led to one of the most influential modern ideas in planetary science, something called the Nice model, named after Nice, France, where it was developed. According to this model, the giant planets originally formed in somewhat different positions than they occupy today. Jupiter may have migrated inward first, Saturn moved too, Uranus and Neptune likely shifted dramatically outward, and those migrations destabilized enormous numbers of smaller objects throughout the solar system. Picture a crowded ice rink where several extremely large skaters suddenly begin changing direction unpredictably. Everything nearby gets disturbed. That is essentially what happened on a planetary scale. Gravity from the migrating giant planets scattered asteroids and icy bodies everywhere. Some objects got thrown into the inner solar system, others were ejected outward entirely. Some may have escaped the sun's gravity forever and drifted into interstellar darkness. And during this period, collisions became extraordinarily common. The late heavy bombardment may partly trace back to this instability. For a long time, scientists debated whether the late heavy bombardment truly occurred as a distinct event or represented a gradual decline in impacts over time. The debate continues in some details even now, but regardless of exact timing, one thing is clear. The young solar system endured prolonged periods of violent instability. The Moon preserves much of this history, because unlike Earth, it lacks oceans, weather, and plate tectonics to erase ancient scars. Its cratered surface acts almost like a fossilized memory of bombardment eras long vanished elsewhere. Looking at the Moon is, in some sense, looking at surviving evidence of the solar system's chaotic childhood. Earth experienced the same impacts. Mars did too. Mercury especially bears heavy bombardment scars. Even the giant planets likely absorbed enormous collisions during formation, and amidst all this gravitational turmoil, planetary spins evolved unpredictably. This is important because the early solar system was not merely chaotic in terms of collisions. Orbital relationships themselves kept shifting. Resonances formed and broke apart. Migration altered gravitational balances. Small differences amplified over time. Astronomy often behaves like an elaborate chain reaction, where one change triggers another, which triggers another, until entire systems reorganize themselves. Jupiter played a particularly enormous role. It is difficult to overstate how influential Jupiter's gravity remains. The planet contains more mass than all the other planets combined. Its gravitational field dominates much of the solar system's large-scale architecture. Some models suggest Jupiter migrated inward toward the Sun early in solar system history, before reversing direction and moving outward again. This idea is sometimes called the Grand Tack hypothesis, named after a sailing maneuver where ships change direction sharply. If true, Jupiter may once have ventured surprisingly close to the inner solar system. Imagine that for a moment. The largest planet in the solar system drifting inward through regions where rocky planets were still forming. Its gravity would have scattered material enormously. Some protoplanets may have been destroyed entirely. Others got thrown into new orbits. The distribution of rocky material changed dramatically. Then Saturn's gravitational influence altered Jupiter's migration, pulling both planets outward again. The giant planets essentially reshaped the solar system while moving through it, and the consequences lasted forever. Mars may partly owe its unusually small size to these migrations. Some models suggest Jupiter disrupted material accumulation in the outer inner solar system, starving Mars of additional mass during formation. Again, one giant planet moving differently may have altered the future evolution of neighbouring worlds permanently. There is something wonderfully unsettling about that. Planetary systems are sensitive. Tiny differences early on produce enormous long-term consequences. A slightly altered orbit here, a collision there, a migration occurring a bit earlier or later, and billions of years afterward, entire worlds look different. Even Earth's existence in its present form may partly depend on these ancient gravitational rearrangements. Without Jupiter's migrations, perhaps the asteroid belt forms differently. Perhaps water delivery changes. Perhaps Earth's growth alters. Perhaps entirely different planets emerge instead. Astronomy constantly reminds us how contingent cosmic history can be. The solar system we know is one outcome among many possibilities, and during its early eras, stability was far from guaranteed. Some simulations of planetary formation produce dramatically different results from our current arrangement. Super-Earths sometimes form in the inner solar system. Giant planets scatter each other into eccentric orbits. Rocky worlds collide repeatedly until only a few survivors remain. Certain systems become catastrophically unstable. Others settle into resonant harmony. The diversity of exoplanet systems discovered in recent decades strongly supports this idea. Planetary systems throughout the galaxy appear remarkably varied. Some contain giant planets orbiting scorchingly close to their stars. Others pack multiple planets tightly together in compact resonant chains. Some worlds follow wildly elongated orbits. Others likely experience violent scattering events, reshaping their architectures completely. Our solar system is not the universal template astronomers once imagined. It is simply one surviving configuration, and perhaps a relatively calm one by galactic standards. That possibility feels strange too, because from a human perspective, the early solar system already sounds unbelievably violent. Worlds colliding, moons forming from planetary debris, asteroids raining across young planets, giant planets migrating unpredictably. Yet elsewhere in the galaxy, even stranger histories may have unfolded routinely. One especially important consequence of the chaotic early solar system involves water. Earth formed relatively close to the Sun, where temperatures likely remained too high for abundant water ice during early formation stages. Yet modern Earth possesses enormous oceans. Where did all that water come from? Scientists think at least some of it may have arrived later through impacts from water-rich asteroids or icy bodies scattered inward during early solar system instability. In other words, ancient gravitational chaos may have helped deliver the ingredients necessary for future oceans. Again, violence and habitability become intertwined. Without planetary migration and bombardment, Earth might be far drier today, perhaps lifeless entirely. The solar system's instability may indirectly have helped create conditions suitable for biology. There is also evidence that giant impacts continued long after planets initially formed. Mercury appears oddly dense, containing an unusually large metallic core relative to its size. One possible explanation is that colossal impacts stripped away much of the planet's original rocky outer layers. Mars bears evidence of giant basin-forming collisions. The moon-forming impact reshaped Earth. Uranus may have been knocked sideways. Venus perhaps reversed spin-through collisions or tidal evolution. Planetary formation was not a clean assembly process, it was survival, and some worlds did not survive at all. Astronomers strongly suspect many protoplanets were destroyed, absorbed or ejected entirely during the solar system's early history. There may once have been additional planets. Some theories even propose a fifth giant planet originally existed before gravitational interactions eventually expelled it into interstellar space. Imagine a whole planet cast out forever, a world wandering dark, between stars because gravitational encounters destabilized its orbit billions of years ago. Rogue planets like this may actually be common throughout the galaxy. Some estimates suggest interstellar space could contain enormous numbers of planet-sized bodies drifting alone without suns. The galaxy may be full of exiled worlds, and all because young planetary systems are chaotic environments. One reason the modern solar system feels so stable now is simply because most of the instability already happened. Over time, gravitational interactions eliminated many dangerous configurations. Collisions merged objects together. Resonances settled into long-term patterns. Surviving planets gradually stabilized. The current arrangement represents the aftermath of billions of years of dynamical evolution. What we see today is what survived. That realization changes how ordinary planetary motion feels. Earth's steady orbit is not inevitable. The Moon's presence is not inevitable. Jupiter's current position is not inevitable. The solar system evolved toward its present state through countless interactions, migrations, impacts, and near disasters, and because those processes unfolded over immense timescales, the surviving scars remain visible everywhere. Cratered moons, tilted planets, retrograde rotations, captured satellites, asteroid belts, comets from distant reservoirs, all preserve fragments of the solar system's chaotic youth. There is something emotionally grounding about this too, oddly enough. Human beings often crave certainty and permanence, yet the universe itself emerged through instability. Order formed gradually out of chaos rather than existing automatically from the beginning. Even planets required time to settle down. Perhaps that is partly why astronomy feels comforting sometimes. Cosmic history reminds us that turbulence and instability are not necessarily signs of failure. They are often part of formation itself. The calm skies above Earth tonight emerged from extraordinary violence long ago, and still, the process never fully ended. Asteroids continue orbiting. Comets still visit the inner solar system occasionally. Gravitational interactions remain active. The planets continue evolving subtly. Nothing is ever completely frozen in celestial mechanics. One especially beautiful example of surviving early chaos appears in the asteroid belt itself. People often imagine the asteroid belt as densely crowded, perhaps because science fiction enjoys dramatic spaceship navigation scenes involving constant dodging of tumbling rocks. In reality, the asteroid belt is mostly empty space, yet it represents material that never formed into a planet. partly because Jupiter's gravity kept disturbing the region too strongly for stable accumulation, a failed planet zone shaped by giant planetary migration. Even absence can preserve history. The Kuiper Belt beyond Neptune tells another story. That distant icy region contains countless remnants from solar system formation. Pluto, Eris, Haumea, Makemake, and many smaller bodies drift there beneath weak sunlight. Their orbital patterns preserve evidence of Neptune's outward migration long ago. Again, the giant planets rewrote the architecture of the solar system as they moved, and the small icy worlds still remember. Perhaps the most remarkable thing about all this is that humans can reconstruct it at all. No one witnessed these events. No ancient civilization observed Jupiter migrating or planets colliding. Yet through physics, observation, computer simulations, crater analysis, orbital mechanics, and careful reasoning, scientists gradually pieced together the story. The solar system became understandable not because it is simple, but because the laws governing motion remain consistent. Gravity leaves evidence, motion preserves memory, and planets carry their histories in rotation, tilt, orbit, composition, and scars. Earth continues moving through a solar system that appears calm only because its wildest eras ended billions of years ago. But the evidence remains everywhere, in Venus rotating backward, in Uranus lying sideways, in Triton orbiting retrograde, in cratered moons and scattered asteroids and wandering comets drifting inward from deep space. The present solar system is the quiet survivor of ancient chaos. For most of human history, the planets of our own solar system were the only worlds we knew. Mercury, Venus, Mars, Jupiter, Saturn, a small local family orbiting one ordinary star. And because humans naturally build expectations from limited experience, astronomers once assumed other planetary systems probably resembled ours closely. A few rocky worlds near the star, giant planets farther out, mostly circular orbits, mostly orderly motion, reasonable, predictable, comfortingly tidy. Then humanity started finding exoplanets, and almost immediately the universe began behaving like it had absolutely no intention of following our assumptions. Some of the first discovered exoplanets already looked bizarre. Giant planets orbited scorchingly close to their stars. Orbits stretched into extreme ellipses. Entire systems appeared dynamically unstable. But perhaps most surprising of all were the retrograde worlds, planets orbiting in directions apparently opposite the rotation of their stars. That discovery forced astronomers to rethink how planetary systems evolve. Because if planets form from rotating disks around young stars, then planets and stars should generally share the same direction of motion. Yet some exoplanets clearly do not. Something violent must have happened there, and suddenly the strange worlds of our own solar system no longer seemed quite so unusual. One of the most famous examples is WASP-17b. Even the name sounds slightly like a robot trying to introduce itself politely. WASP-17b was discovered in 2009, and it quickly became one of the strangest known exoplanets at the time. The planet itself is enormous, a gas giant larger than Jupiter but incredibly puffed up and low in density. In fact, it is one of the least dense planets ever discovered. If you could somehow place WASP-17b into an unimaginably gigantic cosmic bathtub, it would float, which is already fairly unusual behaviour for a planet. But the truly remarkable detail involved its orbit. Astronomers determined that WASP-17b appears to orbit backward relative to the spin of its parent star. Retrograde. This was a major surprise because it challenged simple models of planetary formation. A giant planet was not merely rotating strangely like Venus, it was orbiting the wrong direction entirely. Imagine discovering that Earth moved around the Sun opposite every other planet. That is roughly the level of surprise involved. Scientists immediately began asking how such a thing could happen. One possibility involves gravitational scattering between giant planets. Early in a system's history, multiple massive planets may interact chaotically. Close encounters can fling planets inward, outward, or into highly tilted orbits. Another idea involves something called the Kozai leadoff mechanism, which sounds less like orbital physics and more like an avant-garde law firm. This process occurs when a distant massive companion, perhaps another star or giant planet, gradually disturbs a planet's orbit over immense timescales. The orbit can become increasingly tilted and elongated, until tidal interactions with the star eventually shrink and circularize it into a close retrograde orbit. In simpler terms, gravity slowly destabilizes everything until the planet ends up moving in bizarre directions. Astronomy often reduces to gravity causing trouble creatively. WASP-17b was important because it proved retrograde planetary systems truly exist. Not theoretical curiosities, real worlds orbiting real stars. And once astronomers realized such systems were possible, they started finding more. Another famous example is HATP-7b. This planet orbits a star roughly 1,000 light-years away in the constellation Cygnus. Like many early discovered exoplanets, it is a hot Jupiter, a giant gas planet orbiting extremely close to its star. Its year lasts only about 2 Earth days. Imagine celebrating birthdays every 48 hours. You would age socially at an exhausting pace. But once again, the orbit appears severely misaligned with the star's rotation, possibly even fully retrograde. Observations from the Kepler Space Telescope revealed additional hints that the entire system may have experienced gravitational chaos in the past. Other bodies in the system may have disrupted HATP-7b's orbit over time, gradually tilting it into its current bizarre configuration. The planet likely did not form where it exists today. That became another major realization in exoplanet science. Many giant planets probably migrate dramatically after formation. Hot Jupiters especially could not have formed near their stars because temperatures there would have prevented giant gas accumulation. Instead, they likely formed farther out before moving inward later. And during that migration, gravitational interactions can become chaotic enough to tilt or even reverse orbital orientations. Planetary systems, it turns out, are not static. They evolve dynamically, sometimes violently. The third especially famous example is Kepler-63b. Now this world is fascinating for slightly different reasons. Kepler-63b orbits a very active young star covered in enormous star spots, gigantic stellar equivalents of sunspots. Astronomers studying the planet noticed something remarkable about its orbital geometry. The planet's orbit is dramatically tilted relative to the star's rotational axis, not merely slightly misaligned, wildly misaligned. The planet effectively travels across the star at a steep angle compared to the star's spin orientation. This discovery mattered because it reinforced the growing realization that planetary systems can become severely tilted during formation or evolution. Not every system settles into neat flat alignment like a simplified textbook diagram. Some become twisted, chaotic, misaligned. And once astronomers started looking carefully, they found many more examples. HD80, 1606b possesses an extraordinarily eccentric orbit likely shaped by gravitational interactions. WASP-79b appears strongly misaligned. KELT-9b, one of the hottest known exoplanets, orbits a star so intensely hot that parts of the planet itself may vaporize continuously beneath stellar radiation. Some systems contain planets orbiting binary stars. Others feature compact chains of resonant planets packed tightly together. The diversity became overwhelming very quickly, and importantly, retrograde or highly tilted orbits no longer looked rare. They appeared surprisingly common among certain categories of giant exoplanets. This forced astronomers to reconsider earlier assumptions about planetary system formation. The original rotating protoplanetary disk still matters enormously, of course. Most systems likely begin broadly aligned, but afterward, gravitational interactions can rewrite everything. Planet-planet scattering, stellar companions, migration through disks, tidal evolution, close encounters. Over billions of years, planetary systems become dynamic histories rather than frozen initial conditions. One especially interesting realization is that stars themselves may sometimes contribute to orbital chaos. Young stars can possess tilted magnetic fields and complex rotational behavior. Binary star systems introduce additional gravitational complications. Nearby stellar encounters in dense star clusters may perturb planetary systems early on. The universe does not build planets in isolation. Everything influences everything else eventually. There is something strangely comforting about how messy this all is. Humans often assume the cosmos should behave like a perfectly engineered machine. But real planetary systems resemble ecosystems more than clocks. Complex, interconnected, sensitive to small disturbances, capable of evolving toward radically different outcomes. Even our own solar system likely experienced periods of comparable chaos long ago. We simply see it after billions of years of relative stabilization. Exoplanets allow astronomers to observe other systems at different evolutionary stages. Some may still be actively chaotic now, others perhaps settled long ago. And because the galaxy contains hundreds of billions of stars, the variety becomes staggering. There are probably planets out there with permanent supersonic storms, worlds with oceans beneath global ice crusts, planets orbiting dead stars, gas giants drifting alone through interstellar darkness, and undoubtedly many more retrograde worlds moving beneath alien skies. One particularly strange category involves planets orbiting extremely close to rapidly rotating stars. In some cases, the stars themselves become distorted by rotation, bulging outward at the equator. Radiation varies dramatically across stellar surfaces. Gravity darkening occurs, where equatorial regions cool and dim slightly compared to the poles. Planets moving around such stars experience bizarre environments. Astronomy stopped being simple the moment humans realized planets existed elsewhere. Before exoplanets, theories of planetary formation relied heavily on one example, our own solar system. But once thousands of alien worlds appeared, astronomers suddenly faced an explosion of possibilities, and the universe proved far more imaginative than expected. There is also a philosophical shift hidden inside all this. For centuries, humans naturally treated Earth and the solar system as central reference points. Even after heliocentrism displaced Earth from the centre physically, our planetary system still felt like the default model. Exoplanets destroyed that assumption completely. Our solar system is not the standard. It is one arrangement among countless others, perhaps relatively calm, perhaps even slightly unusual. That realization changes how we interpret worlds like Venus and Uranus too. Backward rotation no longer seems like an isolated curiosity. Sideways planets no longer seem uniquely bizarre. Instead, they become part of a much larger cosmic story about gravitational evolution and planetary instability. Retrograde worlds elsewhere reinforce the idea that planetary systems are shaped not merely by formation, but by survival. The systems we observe today are survivors of ancient interactions. Some worlds got scattered inward, some got ejected, some collided, some became tilted or retrograde, and some settled into temporary stability lasting billions of years. Temporary is important here, because even apparently stable systems continue evolving slowly. One especially beautiful aspect of exoplanet science is how indirect much of the evidence remains. Astronomers usually cannot see these planets directly. Instead, they infer them through subtle effects, tiny dips in starlight as planets transit across stars, minute gravitational wobbles, slight spectral shifts, careful measurements revealing impossible hidden worlds. Retrograde motion itself often gets detected through something called the Rossiter-McLaughlin effect. As a planet crosses its star, it blocks portions of the rotating stellar surface differently depending on orbital orientation. From tiny distortions in starlight, astronomers can determine whether a planet orbits aligned, tilted, or backward. Humanity learned alien worlds move the wrong way by studying faint changes in distant light. That feels wonderfully improbable somehow. There is another curious emotional effect too. The more strange exoplanets astronomers discover, the more Earth feels simultaneously special and ordinary. Special because our world supports life beneath relatively stable skies. Ordinary because planets themselves appear everywhere. The galaxy overflows with worlds. Some are calm, some chaotic, some likely uninhabitable beyond imagination, others perhaps surprisingly Earth-like, and somewhere among them, retrograde worlds continue orbiting stars backward, while giant tilted planets drift through darkness beneath alien atmospheres. The universe is not merely stranger than early astronomers expected, it may be stranger than human intuition naturally allows for at all. And once scientists realized how chaotic planetary systems elsewhere could become, another fascinating question emerged naturally. At some point while learning about Venus, almost everyone asked the same question. Could Earth ever start spinning backward too? It is an understandable thought. Once you discover that planets can rotate the opposite direction, tilt sideways, migrate across solar systems, or get struck by catastrophic impacts, Earth suddenly feels a little less permanently stable than before. The familiar sunrise in the east starts seeming oddly temporary. So let's begin with the reassuring answer first. No, Earth is not going to reverse its spin anytime remotely soon. You can safely plan future mornings without worrying that the sun will suddenly rise in the west next Tuesday. The forces required to reverse Earth's rotation are enormous beyond ordinary comprehension. Our planet contains tremendous angular momentum. Earth is not merely rotating casually. At the equator, the surface moves through space at roughly 1,670 kilometers per hour because of planetary spin. Stopping that motion entirely would already require extraordinary energy. Reversing it would require even more, and importantly, nothing in the modern solar system appears capable of accomplishing this gradually under present conditions. Venus likely reached its strange rotation through a combination of factors operating very early in solar system history, when worlds were still forming and collisions remained common. Earth today exists in a much calmer environment. Much calmer does not mean perfectly safe forever, admittedly. Astronomy rarely promises absolute permanence, but Earth's current rotational state is remarkably stable on human timescales. Still, the deeper question remains fascinating. What would it actually take to reverse Earth's spin? And what would happen if it somehow occurred? The simplest answer involves collisions. A sufficiently large impact could dramatically alter Earth's rotation, just as ancient collisions likely affected Uranus and perhaps Venus. But the scale involved becomes difficult to imagine comfortably. The moon-forming impact probably changed Earth's rotation significantly long ago. Yet even that collision did not reverse the planet completely. To flip Earth's spin entirely today, an object perhaps comparable in size to Mars would likely need to strike under very particular conditions. And if such an event happened, sunrise direction would become the least immediate concern. The impact itself would be catastrophic beyond anything human civilization could survive. Entire oceans would vaporize. The atmosphere would heat enormously. Shock waves would circle the planet repeatedly. Much of Earth's crust could melt. In other words, technically possible in physics terms, but not something worth adding to your everyday anxiety collection. Astronomy contains many scenarios best appreciated theoretically. There are gentler possibilities too, though none realistic anytime soon. Over extremely long periods, gravitational interactions can alter planetary rotation gradually. Tidal forces already slow Earth's spin slightly because of the Moon. billions upon billions of years from now, Earth's day length will continue increasing. Eventually, if the Sun somehow remained stable long enough, Earth and the Moon might approach tidal synchronization, where one Earth hemisphere permanently faced the Moon. But the Sun will evolve into a red giant long before such a state fully develops. Stellar evolution interrupts many long-term planetary futures. Again, the universe rarely allows systems to remain static forever. There's another interesting layer to this question too. Earth's rotation has reversed in a limited sense before, at least magnetically. The planet's magnetic poles periodically flip through processes occurring in Earth's liquid outer core. North becomes south, south becomes north. This happens irregularly over geological time. Importantly, these magnetic reversals do not involve the planet physically changing spin direction. Earth keeps rotating normally. Compasses simply would behave very differently afterward. Still, magnetic reversals likely contributed to public confusion around planetary flipping because they sound dramatic and slightly apocalyptic. Human imagination tends to enjoy dramatic celestial events, perhaps a little too enthusiastically sometimes. The actual physical reversal of Earth's rotation would produce astonishing consequences. Let's imagine it hypothetically for a moment, not through sudden catastrophe necessarily, but as a thought experiment. Suppose Earth somehow gradually began spinning the opposite direction while retaining similar rotational speed. Immediately, many familiar atmospheric and oceanic systems would change profoundly. The Coriolis effect, produced by Earth's rotation, governs large-scale circulation patterns in the atmosphere and oceans. Hurricanes rotate differently in opposite hemispheres partly because of it. Jet streams follow specific paths because of it. Reverse Earth's spin, and those systems reorganize dramatically. Trade winds would reverse direction. Ocean currents would shift. Climate zones could change significantly. Deserts and rainforests might redistribute over geological time. The Gulf Stream, which helps moderate European climate today, could weaken or alter course entirely. Weather itself would feel alien compared to modern Earth. Even the night sky would seem subtly different over time because of how celestial motion appears relative to Earth's rotation. And of course, the sun would rise in the west. That detail still feels psychologically strange despite all the larger consequences involved. Human civilization is deeply structured around ordinary directional expectations. East and West carry cultural meaning. Architecture often aligns with sunlight patterns. Navigation traditions developed beneath familiar skies. Religious symbolism, art, language, and myth all absorbed Earth's rotational rhythm over thousands of years. A reversed Earth would produce different civilizations because the environment itself would shape human history differently from the beginning. That point is important. Planetary rotation does not merely influence astronomy. It influences biology, weather, sleep, migration, agriculture, navigation, and culture. Earth's present spin quietly structures human existence constantly. The length of a day affects circadian rhythms. Atmospheric circulation shapes ecosystems. Ocean currents redistribute heat globally. Everything interconnects. One especially interesting consequence of Earth's rotation involves the equatorial bulge. Because Earth spins, centrifugal effects push material outwards slightly around the equator. The planet is not perfectly spherical. It bulges outward by about 43 kilometers at the equator relative to the poles. If Earth stopped rotating entirely, that bulge would gradually relax. Oceans would redistribute dramatically toward the poles. Entire coastlines would change. Sea levels would shift enormously. Again, planetary rotation shapes far more than sunrise direction. Even gravity itself varies slightly because of spin. You weigh a tiny bit less at the equator than at the poles due to centrifugal effects. Not enough to solve anyone's fitness concerns, unfortunately, but measurable. Astronomy often reveals ordinary experiences resting atop hidden planetary mechanics. There's another curious aspect to Earth's rotation too. The planet already wobbles slightly, not dramatically enough to notice directly, but Earth's axis shifts gradually over time through processes called precession and nutation. Precession occurs because gravitational forces from the Moon and Sun tug on Earth's equatorial bulge. The rotational axis slowly traces a circular motion over about 26,000 years. Ancient Egyptians observed different pole stars than we do because of this. In the future, different stars will occupy the northern sky again. Earth's orientation changes continually, just very slowly. And sometimes major geological events alter rotation slightly too. Large earthquakes can redistribute enough mass to change Earth's rotation by tiny measurable amounts. The 2004 Indian Ocean earthquake shortened Earth's day by microseconds. Again, the planet is dynamic, not frozen, always evolving subtly beneath human awareness. Could humans themselves ever intentionally reverse Earth's spin? No, at least not with any technology remotely imaginable. The energies involved are absurdly large. Even humanity's entire global energy production becomes insignificant compared to Earth's rotational energy. Science fiction occasionally enjoys exploring such ideas, usually with alarming consequences, but physics remains deeply unimpressed by human engineering ambitions at planetary scales. Earth is enormous. Sometimes astronomy provides useful perspective that way. Still, the question persists because retrograde worlds challenge intuitive assumptions about stability. Once humans learn planets can spin backward, ordinary planetary motion stops feeling guaranteed, and that realization contains an important scientific lesson. Planetary systems evolve. Earth's current state is not eternal, not fragile exactly, but temporary in cosmic terms. The atmosphere changes over geological time. Continents drift. The moon moves away gradually. The sun grows brighter slowly. Rotation evolves. Everything planetary exists within long-term processes. Even the familiar length of a day is historically contingent. Hundreds of millions of years ago, Earth spun faster. Hundreds of millions of years from now, it will spin more slowly. Dinosaurs experience shorter days than humans do today. Future creatures, if any exist, may live beneath longer ones. Earth itself preserves evidence of these ancient rotational changes in certain geological formations. Some tidal sediment patterns record past day lengths indirectly. Fossil corals preserve daily growth rings revealing how many days existed per year long ago. The planet remembers its changing spin. There is something oddly calming about this broader perspective. Human lives unfold within relatively stable environmental conditions, so it is easy to imagine Earth itself as fixed and permanent. Astronomy gently disrupts that illusion. Not catastrophically, just honestly. Planets evolve, worlds change, the cosmos remains dynamic. Yet Earth's stability over human timescales remains extraordinary too. For all the chaos of planetary formation, our world settled into conditions gentle enough for life to flourish over billions of years. The moon stabilized Earth's tilt. The atmosphere remained relatively moderate. Liquid water persisted. The rotation stayed fast enough for balanced temperature distribution, but slow enough for stable climates. Earth may not be eternal, but it has been remarkably accommodating, which perhaps explains why backward-spinning worlds like Venus fascinate us so much. They represent alternate planetary paths, reminders that Earth could have evolved differently under slightly altered conditions, a different impact here, a different atmosphere there, a different tidal history, and perhaps our own world might feel far stranger today. Some exoplanets almost certainly do experience rotational states wildly different from Earth's. Tidally locked worlds, retrograde planets, worlds rotating so slowly that days last months, others spinning rapidly enough to distort their own shapes dramatically. The universe experiments with planetary motion constantly. Earth simply occupies one relatively comfortable outcome among many possibilities. Tonight our planet continues spinning eastward beneath familiar stars exactly as generations before us experienced. Sunrise tomorrow will arrive where humans expect it to. Meanwhile, Venus rotates backward through toxic clouds. Uranus rolls sideways beneath pale sunlight. Retrograde exoplanets orbit distant stars the wrong direction entirely. And gravity continues patiently reshaping planetary motion everywhere across the galaxy. One of the strangest things about the universe is how often enormous changes happen quietly. Not through explosions, not through sudden disasters, but through tiny effects repeating patiently for billions of years. Tidal forces are a perfect example. At first glance, tides seem harmless enough. Gentle ocean motion, water rising and falling along coastlines. Something associated more with beaches and calendars than with planetary evolution. But tides are actually one of the most powerful long-term mechanisms in celestial mechanics. Given enough time, tidal forces can slow planetary rotation, lock moons into synchronization, heat entire worlds internally, alter orbits, create geological activity, and even destroy moons completely. All without violence in the ordinary sense, just gravity working persistently across distance. The key to understanding tides is realizing that gravity weakens with distance. This sounds simple, but the consequences become extraordinary. Imagine the moon pulling on Earth. The side of Earth closest to the moon experiences slightly stronger gravitational attraction because it is nearer. The far side experiences slightly weaker pull because it is farther away. That difference stretches Earth subtly, not dramatically enough to notice while walking around, thankfully. The planet is not wobbling visibly like gelatin beneath your feet. But the stretching is real. The oceans respond especially easily because water moves freely. This creates tidal bulges. One bulge forms on the side facing the moon. Another forms on the opposite side due to the way Earth and Moon orbit their shared center of mass. As Earth rotates, coastlines move through these bulges, producing the rising and falling tides humans experience daily. For most of history, tides seemed almost mystical. Ancient civilizations tracked them carefully because they mattered enormously for fishing, navigation, and coastal life. Yet their true origin remained mysterious until gravity itself became understood properly. Today we know tides are not merely local ocean behavior. They are visible evidence of gravitational interaction between worlds. The moon physically reshapes Earth slightly every single day, and Earth reshapes the moon too. That mutual stretching matters because moving material generates friction. The oceans drag against coastlines and sea floors. Energy dissipates as heat. Rotation loses tiny amounts of momentum. Again, the effect is extremely small over human lifetimes. But astronomy operates on scales where tiny effects become transformative. Earth's rotation gradually slows because of tidal friction. The moon gradually moves farther away. This process has been happening for billions of years, which means Earth's days used to be shorter, much shorter. Shortly after the moon formed, Earth may have rotated once every 5 or 6 hours. Imagine sunsets arriving 4 times faster than today. The young Earth would have felt astonishingly dynamic. Powerful winds, rapid weather cycles, frequent day-night transitions, the sky itself moving at unfamiliar speed. Over time, tidal forces applied invisible brakes. Slowly, relentlessly, day length increased, and it continues increasing still. Dinosaurs lived beneath faster spinning skies than humans do. That realization never stops feeling slightly surreal. One of the most ordinary aspects of life, the length of a day, turns out not to be permanent at all. Earth is evolving rotationally. The moon preserves evidence of this relationship beautifully. Because Earth rotates faster than the moon orbits, tidal bulges get pulled slightly ahead of the moon's position. Those bulges exert gravitational pull on the moon itself, transferring rotational energy outward. As a result, the moon gains orbital energy and slowly recedes from Earth. By about 3.8 centimeters per year. Tiny, yet over geological timescales, enormous. The moon once appeared larger in Earth's sky. total solar eclipses looked different in the distant past. Eventually, billions of years from now, the moon will drift far enough away that perfect total eclipses disappear entirely. Humanity happens to exist during a temporary era when the moon and sun appear almost exactly the same size in the sky. That coincidence itself feels improbable enough already, but tides become even stranger elsewhere in the solar system. Take Io, one of Jupiter's moons. Io is perhaps the most volcanically active world known. Hundreds of volcanoes erupt across its surface continuously. Lava lakes bubble beneath sulfur-rich landscapes. Enormous plumes rise hundreds of kilometers into space, and the energy source driving all this chaos is tidal force. Jupiter's gravity stretches Io intensely because the moon orbits extremely close to the giant planet. But there's another complication. Europa and Ganymede, neighbouring moons, gravitationally tug on Io as well. These interactions prevent Io's orbit from becoming perfectly circular. Instead, the moon experiences slight orbital variations that continually flex and distort it. Imagine squeezing a rubber ball over and over again. The internal friction generates heat. Io experiences this on a planetary scale. The entire moon gets kneaded gravitationally. Its interior melts. Volcanoes erupt endlessly. Tidal forces transformed a frozen moon-sized body into a volcanic nightmare. Again, gravity accomplishes astonishing things through persistence. Europa experiences similar tidal flexing too, though less extreme. Scientists think this heating helps maintain a vast liquid ocean beneath Europa's icy crust. That hidden ocean may contain more water than all Earth's oceans combined, and because liquid water plus energy creates interesting possibilities scientifically, Europa remains one of the most compelling places in the solar system in the search for extraterrestrial life. All because of tides. Enceladus, a moon of Saturn, tells a comparable story. Despite its small size and icy surface, Enceladus sprays enormous geysers of water vapour and ice particles into space from cracks near its south pole. A global subsurface ocean likely exists beneath the ice. Once again, tidal heating appears responsible. Saturn's gravity flexes the moon repeatedly, generating internal warmth. Invisible gravitational stretching creates underground seas beneath frozen crusts. The universe hides oceans in remarkable places, and tidal forces do not merely create heat, they reorganize motion itself. Most large moons in the solar system are tidally locked. The moon always shows the same face to Earth because tides gradually synchronized its rotation with its orbit. 1 lunar day equals 1 lunar month. This outcome is so common that astronomers almost expect it automatically now. Given enough time, tides prefer synchronization. Mercury presents another fascinating case. The planet is not fully tidally locked to the Sun, but it occupies a 3-to-2 spin-orbit resonance. Mercury rotates 3 times for every 2 orbits around the Sun. Solar tidal forces gradually shaped this arrangement over immense timescales. Without tides, Mercury likely would spin differently today. Venus may also owe much of its bizarre rotation to tidal evolution. Its thick atmosphere creates complex atmospheric tides as sunlight heats different regions unevenly. Combined with solar gravitational effects, these forces may have gradually slowed and reversed Venus's rotation over billions of years. Imagine an entire planet slowly turning backward because of sunlight interacting with atmosphere and gravity. Astronomy frequently sounds impossible until physics quietly confirms it. There is another important consequence of tidal forces too. They can destroy worlds, or at least moons. Earlier we discussed Triton spiralling inward toward Neptune because of retrograde orbiting. Mars's moon Phobos faces a similar fate. Phobos orbits Mars faster than Mars rotates. This means tidal interactions pull the moon inward rather than outward. The moon slowly approaches Mars. Eventually, tidal forces may tear it apart into rings or crash it into the planet entirely. A moon doomed by gravity. The solar system contains many long-term stories unfolding too slowly for humans to notice directly. One especially eerie possibility involves exoplanets orbiting very close to their stars. Many hot Jupiters circle their stars in only days. Tidal forces there become immense. Some planets may already be tidally locked with permanent day and night hemispheres. Others could be spiraling slowly inward toward destruction. Eventually, certain close-orbiting planets may cross their star's Roche limits and get torn apart by stellar gravity itself. Imagine a planet stretched into streams of vaporized material as gravity overwhelms structural integrity. Tidal forces scale upward dramatically in extreme environments. Near black holes, they become terrifying. The phrase spaghettification exists because of tidal gravity. Close to a black hole, gravitational pull on the near side of an object becomes vastly stronger than on the far side. The result is catastrophic stretching. A human falling into a small black hole would eventually be pulled apart into elongated streams of matter. Not an especially relaxing bedtime image perhaps, though fortunately black holes tend to remain respectfully distant. Still, the same basic physics creating gentle ocean tides on Earth also powers some of the most extreme processes in the universe. That connection feels deeply strange. There's something philosophically beautiful about tidal forces too. They remind us that relationships matter in astronomy. Planets do not evolve independently. Moons influence planets. Planets influence moons. Stars influence planets. Everything interacts gravitationally. Earth's rotation changes because the moon exists. Io erupts because neighbouring moons perturb its orbit. Europa may contain oceans because Jupiter flexes it repeatedly. Planetary history emerges from interaction rather than isolation. Even life on Earth may partly owe its existence to tidal processes. Tides influence coastal chemistry on the early Earth. The moon stabilized Earth's axial tilt. Ocean cycles shaped ecosystems for billions of years. Gravity quietly structured conditions favorable for biology long before humans understood what tides even were. And because tides operate slowly, they become easy to underestimate. Human minds naturally focus on dramatic immediate events. Yet many of the universe's greatest transformations happen almost invisibly across deep time. Mountains erode grain by grain. Continents drift centimetre by centimetre. Planets slow rotation millisecond by millisecond. The universe is patient enough for tiny changes to become enormous. There's another curious consequence of Earth's tides too. The oceans themselves help stabilise climate through circulation patterns, influenced partly by rotation and lunar interaction. Tidal mixing affects nutrient distribution and marine ecosystems. Some marine species synchronise behaviour with tidal cycles and moon phases. Even biology dances partly to gravitational rhythms. The moon shapes Earth more profoundly than most people realise. Without it, nights would look different. Tides would weaken enormously. Earth's rotation would remain faster. Axial stability might decrease. Human culture itself would have evolved differently beneath altered skies, all because of tidal interaction between two worlds. That realization changes how ordinary moonlight feels somehow. The moon is not merely an object hanging decoratively overhead. It is an active participant in Earth's evolution. By now, the solar system probably feels a little less orderly than it did at the beginning of tonight's journey. At first, the planets seem almost predictable. Worlds orbiting neatly around the sun in graceful patterns inherited from one ancient rotating cloud. A giant cosmic system moving together with quiet cooperation, and then the exceptions begin appearing. Venus turns backward beneath crushing clouds. Uranus rolls sideways through darkness as though some forgotten collision knocked it permanently off balance. Triton circles Neptune in reverse like a captured intruder that never truly belonged there. Distant exoplanets orbit their stars along impossible angles. Entire planetary systems drift through configurations no early astronomer would ever have predicted. The more closely we look at the universe, the less it resembles a perfect machine. And oddly enough, that may be one of the most comforting things about it, because space is not frozen, not rigid, not carefully arranged into flawless symmetry. The cosmos is dynamic, chaotic, full of history. Worlds collide, moons get captured, planets migrate, rotations tilt and drift and sometimes reverse completely. Every strange orbit and backward sunrise tells a story about something ancient that once happened long ago. A collision, a gravitational encounter, a slow tidal evolution unfolding patiently across billions of years. The planets themselves become historical records. That idea changes how motion feels. Earth spinning beneath you tonight is not merely happening in the present moment. It is part of a chain of events stretching backward to the birth of the solar system itself. Our world still carries momentum inherited from a collapsing molecular cloud, older than oceans, older than mountains, older than life. Tomorrow morning's sunrise will happen because of motion established before Earth fully existed. And meanwhile, elsewhere in the darkness, countless other worlds spin according to entirely different histories. Some rotate so slowly that days last longer than years. Some may keep one hemisphere trapped in eternal daylight. Others likely tumble chaotically beneath alien skies, unlike anything humans have ever experienced. The galaxy appears full of worlds that refuse to remain simple. There is something quietly humbling about realizing how unusual Earth actually is, not unique necessarily, but balanced. Our rotation is fast enough to produce stable climate circulation, but not so fast that storms become unimaginably violent. The moon stabilizes Earth's tilt. The day-night cycle supports biology comfortably. Oceans redistribute heat efficiently. So many conditions align together in ways humans usually take completely for granted. Only after studying strange planets do we fully appreciate how many other outcomes were possible. Earth could have spun backward, could have tipped sideways, could have lost its moon, could have become another Venus beneath a runaway greenhouse sky. The universe had many ways our world might have turned out differently, and yet, here we are. A species of curious mammals lying beneath blankets and rooftops on one rotating planet, asking questions about worlds billions of kilometers away. That alone is extraordinary. Because the universe did not need observers. Gravity would still shape planets without us. Stars would still form and die. Galaxies would still drift through darkness. Venus would still rotate backward whether anyone noticed or not. And yet consciousness emerged on at least one small rocky world capable of studying the motion itself. Creatures made from atoms forged inside ancient stars learned how to measure planetary spin. That may be the strangest thing in astronomy. Not black holes, not retrograde worlds, not giant planets migrating through solar systems, but the fact that matter can eventually wake up enough to wonder where it came from. Tonight, somewhere beyond your ceiling, Earth continues turning eastward through space, exactly as it has throughout all of recorded human history. The moon keeps pulling gently at the oceans. Jupiter's gravity still shapes distant asteroids. Neptune carries Triton backward through the cold outer darkness, and around other stars countless unseen planets continue spinning in directions humans have never witnessed directly. Some of them are probably calm, others likely chaotic, a few perhaps beautiful in ways impossible to imagine properly. The universe never spins quite the way we expect, and maybe that is why astronomy remains so endlessly fascinating. Every time humans think we understand the cosmic pattern, another strange world appears to complicate the picture. A planet too large, a moon orbiting backward, a star system tilted sideways, a world with glass rain or eternal storms or years lasting centuries. Reality consistently turns out more creative than human assumptions. There is comfort in that too, because uncertainty does not necessarily make the universe colder or emptier. Sometimes it makes it richer. The sky above Earth tonight is not static scenery. It is the visible surface of an ongoing story still unfolding everywhere simultaneously. Planets continue evolving, orbits continue shifting, tidal forces continue slowing rotations imperceptibly. Gravity keeps shaping worlds patiently across timescales so large they soften ordinary worries slightly around the edges. Not erase them entirely, of course. Astronomy remains unfortunately ineffective at answering emails or folding laundry. Science continues working on these mysteries. Still, perspective matters, and few things provide perspective like realizing that entire planets can spend billions of years rolling sideways through darkness because of collisions older than multicellular life. The cosmos is vast enough to make human urgency feel gentler for a little while. Perhaps that is partly why people have always looked upward at night, not merely out of curiosity, but because the sky changes the scale of thought itself. The stars remind us that existence extends far beyond schedules and clocks and ordinary routines. Somewhere out there, worlds spin backward beneath alien suns while galaxies drift across intergalactic darkness. An ancient starlight crosses unimaginable distances simply to reach human eyes for one brief moment. And for a little while tonight, you became part of that larger story too. You followed the strange paths of retrograde planets. You visited sideways worlds. You drifted through the violent birth of the solar system and watched gravity slowly rewrite planetary motion across billions of years. Not bad for one evening beneath Earth's familiar sky. So wherever you are listening from tonight, whether the night outside your window is quiet or rainy or filled with distant city lights, I hope this journey through the strange spinning worlds of the universe brought you a little calm, a little wonder, and perhaps a slightly different feeling the next time you look upward. Because now you know something easy to forget during ordinary days. The ground beneath you is moving. Earth is turning through darkness right now, and out there among the stars countless other worlds are turning too, each carrying histories stranger than anyone once imagined. Sleep well, and let the universe keep spinning softly around you for a while longer.